Before we move forward, let me ask you something. What if the force that holds your feet to the ground is not the simple pull you once imagined, but the silent architect of every journey humanity has ever taken beyond Earth? What if the familiar weight you feel each morning is only the faintest whisper of a deeper curvature in the fabric of space itself? And if every rocket that has ever risen from a launch pad fought not just air and fire, but the shape of space-time around our planet, then what else might gravity be shaping without our awareness? Could it be that our greatest barrier to exploration is not distance, but the invisible well we live inside? A well carved by mass long before we understood what it meant to escape it. Gravity begins as a sensation so ordinary that it rarely earns a second thought. Yet the moment humanity looked upward and wondered how to reach the sky, gravity revealed itself as the first and most unyielding obstacle. Every object on Earth, whether a falling apple or a spacecraft poised on a launch pad, feels the same inward pull born from the mass of our planet curving the space around it. Newton described this pull as a universal attraction, a force that grows with mass and weakens with distance. His equations captured the motion of planets and the falling of stones with remarkable accuracy, giving scientists a mathematical language to quantify the invisible tether binding Earth to every object near it. Centuries later, Einstein would refine this picture, showing that gravity is not a force reaching across emptiness, but the shape of space-time itself responding to mass and energy. These ideas may seem abstract, yet every rocket launch in history is a direct confrontation with these realities. To leave Earth requires more than strength or momentum. It demands escape velocity, a threshold where an object's kinetic energy becomes great enough to climb out of the gravitational well without being pulled back. For our planet, this speed is roughly 11 kilometers per second, a figure derived from the balance between gravitational potential energy and the energy required for departure. 11 kilometers per second is not a suggestion or a target, but a fundamental physical requirement imposed by the mass and radius of Earth. No rocket can cheat this boundary. It must either reach this speed or accumulate enough sustained thrust over time to achieve the same total energy. This is why spaceflight remains one of the most energy-intensive challenges humanity has undertaken. When the Russian schoolteacher Konstantin Tsiolkovsky began exploring the mathematics of rocketry, he understood that the only way to reach such speeds was through staged propulsion and high exhaust velocity. His rocket equation describes how a vehicle's change in velocity depends on the speed of its exhaust and the ratio of its initial mass to its final mass after burning propellant. This simple yet profound relationship reveals an unavoidable truth. To gain even a modest increase in velocity, a rocket must carry exponentially more propellant. The equation does not care about human ambition or engineering ingenuity. It only reflects the unyielding demands of physics. As a result, early pioneers such as Robert Goddard and Hermann Oberth focused their efforts on improving engine efficiency and understanding how to shed mass during flight, giving birth to the concept of multi-stage rockets. Even today, modern launch vehicles follow the same principles. The towering rockets that lift satellites, astronauts, and exploration probes into space begin their journeys as immense tanks of propellant with a comparatively tiny payload on top. Most of their mass is consumed in the first few minutes of ascent, sacrificed to climb against gravity and pierce the dense lower atmosphere. Data from NASA and other space agencies consistently show that more than 90% of a launch vehicle's initial mass is propellant, a necessary consequence of the energy required to escape Earth's gravitational hold. The flames and thunder of a rocket launch are the dramatic surface of a deeper reality. Humanity is not simply pushing upward, but pushing against the curvature of space-time itself. Newton's insights were tested and confirmed as telescopes improved and celestial measurements grew more precise. Planetary motions matched his predictions with astonishing fidelity, affirming that the same force guiding a falling object governs the orbit of the Moon. Yet Einstein's theory of general relativity revealed the deeper geometry behind these motions. Instead of imagining gravity as an invisible rope pulling objects inward, relativity frames planets and stars as shaping the space around them, creating pathways that other bodies follow. This interpretation aligns with observations such as the bending of starlight during solar eclipses and the precise timing of planetary orbits. While rockets do not directly rely on relativity to leave Earth, the theory enhances our understanding of why escape velocity has the value it does, and why no rocket can bypass the energy cost required to climb away from Earth's mass. Every milestone in the history of spaceflight has carried the imprint of gravity's terms and conditions. The early V-2 rockets of the mid-20th century demonstrated that liquid propulsion could generate the sustained thrust required to rise dramatically through the atmosphere. Later, the American Saturn V and the Soviet N-1 rockets took these lessons to unprecedented scales, harnessing the power needed to send humans beyond low Earth orbit and toward the Moon. Each success and each failure served as a reminder that gravity is indifferent to intention. It accepts only the currency of energy and momentum. As the engines thunder and the structure of a rocket vibrates during ascent, the vehicle is engaged in a precise negotiation with gravity. The thrust must exceed the weight of the rocket at every moment to continue rising, and the trajectory must gradually curve to build horizontal velocity. Achieving orbit is not simply flying upward, but accelerating sideways at such speed that Earth's surface curves away beneath the spacecraft at the same rate it falls. This subtle truth explains why rockets do not shoot straight up, but follow an arcing path called a gravity turn, a maneuver that optimizes efficiency by aligning thrust with the natural path dictated by physics. The deeper one investigates spaceflight, the clearer it becomes that gravity sets the rules for every stage of the journey. It dictates how much propellant must be carried, how engines are designed, how structural loads are distributed, and how staging occurs. It even sets constraints on which missions are feasible with current technology. These constraints are not obstacles born of engineering limitation, but expressions of the fundamental fabric of the universe. Gravity is not the enemy, but the environment. And yet, once a spacecraft has gathered enough speed and direction to remain suspended in motion around Earth, a new challenge emerges. Staying in orbit is not a matter of defying gravity, but obeying it with exquisite precision. That next chapter begins the moment escape is achieved, when the battle against gravity transforms into a delicate dance within its grasp. The moment a spacecraft settles into orbit, something profound changes in its relationship with Earth. It is no longer climbing out of the gravitational well, but sliding gracefully along the curved contours carved by the planet's mass. The engines that roared moments ago now fall silent, leaving only the whisper of motion sustained by momentum. The spacecraft continues falling toward Earth, yet the ground perpetually curves away beneath it, creating a state of continuous freefall that we call being in orbit. This idea often feels counterintuitive because daily experience teaches us that falling is brief and ends abruptly. But in orbit, falling becomes a form of flight, an endless arc shaped by gravity's steady pull and the object's sideways speed. This delicate balance was first understood through Newton's thought experiment of a cannonball launched from a mountain. If fired gently, it falls nearby, but if fired with enough horizontal velocity, it circles Earth without ever touching the ground. Modern spacecraft follow the same principle, merely refined with decades of engineering and mission experience. To remain in this suspended state, a spacecraft must achieve a very specific horizontal velocity. For low Earth orbit, this is roughly 7 km per second, a pace fast enough to circle Earth in a period of about 90 minutes. Every mission from the first satellites to the International Space Station relies on these precise orbital mechanics. Tiny deviations in speed or altitude accumulate over time, making occasional corrections necessary. Atmospheric drag, even at several hundred kilometers above the surface, exerts a faint yet persistent slowing effect that gradually pulls a spacecraft downward. This drag varies with solar activity, which heats the upper atmosphere and causes it to expand. When the atmosphere swells, drag increases, and orbital decay accelerates. Satellites must therefore carry small reserves of propellant for reboost maneuvers, nudging themselves back into stable trajectories. The International Space Station provides a vivid example of humanity's ongoing conversation with gravity. Orbiting at an altitude of roughly 400 kilometers, it experiences enough drag that its orbit must be raised several times each year. Visiting spacecraft such as the Russian Progress resupply vehicles perform these reboost burns, adding small increments of velocity to counteract orbital decay. Without these regular adjustments, the station would slowly spiral downward until Earth's atmosphere claimed it. Even in orbit then, gravity remains present and active, shaping motion through subtle tugs that demand constant attention. As engineers model these orbital behaviors, they rely on the same universal law that governs both falling apples and circling moons. The gravitational attraction between Earth and the spacecraft determines its acceleration toward the planet. Meanwhile, the spacecraft's sideways velocity determines how quickly it moves across the curvature of Earth. When these two influences align perfectly, a stable orbit is born. When they do not, the orbit shifts, elongates, or degrades. Elliptical orbits, where a spacecraft's altitude varies throughout its path, require even more careful planning. At the closest point to Earth, known as perigee, gravity pulls more strongly, causing the spacecraft to accelerate. At the farthest point, apogee, gravity weakens and velocity decreases. Missions use these natural variations to their advantage when adjusting orbital shape or timing. Understanding these principles allows mission designers to choreograph complex trajectories that meet scientific and operational goals. Weather satellites in geostationary orbit must match the rotation of Earth, requiring a circular path at an altitude near 36,000 kilometers. In this distant realm, a spacecraft completes one revolution per day, appearing motionless above a single point on the equator. Navigational satellites, such as those in the Global Positioning System, occupy medium Earth orbit, where their altitude and orbital period provide optimal coverage for timing and positioning signals. Meanwhile, Earth-observing satellites often follow polar or sun-synchronous orbits, crossing the poles while maintaining a consistent angle relative to the Sun. This design ensures that lighting conditions remain uniform across repeated passes, allowing scientists to compare images taken days, months, or years apart. Although these orbital regimes serve very different purposes, they all operate within the gravitational framework that Newton described and that modern measurements confirm. Even astronauts inside the International Space Station experience gravity at nearly the same strength as people on the ground. They float not because gravity has vanished, but because everything around them falls together at the same rate. This shared freefall creates the sensation of weightlessness, a unique environment that reshapes both physics experiments and the human body. But through every moment of a mission, whether a satellite is imaging clouds, a telescope is collecting faint starlight, or a crew is conducting experiments in microgravity, the underlying reality remains the same. Orbit is not an escape from gravity, but a continuous partnership with it, one that depends on precision and unwavering attention to detail. The path that brought spacecraft to this delicate balance began with the enormous energy investment of launch. The path that will eventually take them beyond Earth entirely requires even more careful alignment of gravity, momentum, and timing. Leaving orbit to travel to the Moon, Mars, or any distant destination demands a deeper understanding of how gravity shapes motion not only near Earth, but across the entire solar system. The spacecraft must navigate a complex landscape where the gravitational influence of each planet becomes both a challenge and an opportunity. And it is in that broader realm, where trajectories weave through the interconnected wells of planetary masses, that the next part of this chapter will lead. The spacecraft that drifts silently in orbit, tracing its path through the thin upper edges of Earth's atmosphere, is not meant to remain there forever. Orbit is only a temporary plateau between the heavy pull of the ground and the wider reaches of the solar system. To leave that plateau, a spacecraft must perform another delicate act of balance, one that transforms its orbital motion into the first steps of interplanetary travel. Every mission that has ever ventured beyond Earth has relied on the same fundamental principles. A spacecraft must alter its velocity in just the right direction and by just the right amount to escape Earth's gravitational influence and enter the sweeping pathways that connect planets. This process demands not brute force, but a precise understanding of how momentum and gravity interplay across vast distances. In the early years of rocketry, mission planners learned that adding speed at the right point in an orbit could raise a spacecraft's path until it stretched outward toward the moon or deeper into space. This change in velocity, often called a burn, might last only seconds, but has consequences that unfold over countless kilometers. The spacecraft, once content to circle Earth endlessly, begins spiraling outward as the gravitational tug weakens with distance. Yet even as Earth's pull diminishes, it never disappears entirely. The spacecraft carries with it a history of the forces that lifted it from the launch pad and the momentum it has accumulated during its time in orbit. Every gram of propellant burned to make this transition reflects a careful calculation, one rooted in the same physics that governed its ascent through the atmosphere. When missions target the moon, the required trajectory traces a gentle outward curve intersecting the lunar orbit at a moment when the moon arrives at the same point. Timing becomes a form of choreography, an alignment of motions set by celestial mechanics. If the burn occurs too early or too late, the spacecraft arrives where the moon is not, slipping past its target with no chance of capture. This need for precision underscores the fact that gravity rules not only the beginning of the journey, but every transition that follows. The spacecraft must first escape Earth's immediate grasp, then enter the gravitational domain of another world, shifting loyalty from one mass to another without ever drifting freely. Every calculated maneuver reflects a clear understanding of how mass curves space and how objects respond to that curvature with motion. When missions travel beyond the lunar realm, the gravitational landscape becomes richer and more complex. Earth's gravity fades gradually, blending with the subtle pull of the sun. In this region, spacecraft no longer orbit Earth, but become companions to our star, sharing its gravitational influence with the planets that follow their own elliptical paths. The spacecraft's trajectory stretches into a new equilibrium, one shaped by its velocity and the sun's immense gravitational well. If mission designers wish to reach Mars, Venus, or any other planet, they must shape the spacecraft's path to intersect the orbit of their destination at the exact moment the planet will be there. This dance requires not only knowledge of where planets are, but where they will be months or years in the future. The equations guiding these predictions arise from Newton's laws and from centuries of astronomical measurement, each detail refined by observations of planetary motion and spacecraft tracking data. The energy required for these maneuvers remains a direct legacy of the gravitational well that the spacecraft originally climbed. Earth's mass dictates how much propellant the rocket carried at launch, how efficiently its engines had to operate, and how carefully its stages were designed. Once the spacecraft enters solar orbit, those earlier choices continue to shape its future. A mission with ample fuel reserves can adjust its trajectory with more freedom, performing corrective burns and refining its path. A mission with limited propellant must rely more heavily on gravity itself, using the pulls of planets to redirect its motion. In both cases, gravity remains the central architect of every possibility, offering pathways but demanding precision. The history of exploration offers many examples of how sensitive these journeys are to initial conditions. The Apollo missions relied on meticulously calculated burns to guide their craft from Earth orbit to the Moon. Even a slight misalignment in the timing or direction of those burns could have required additional corrections or jeopardized the mission entirely. Later probes traveling to the outer planets depended on even finer accuracy. Their voyages spanned years, and billions of kilometers, yet a mistake made near Earth could echo outward, amplifying as the spacecraft drifted through the solar system. This sensitivity arises because trajectories are not simple lines, but curves woven through a gravitational landscape that changes with position and velocity. Precision in navigation is not merely a matter of human skill. It reflects the inherent structure of physics, the same structure that governs falling objects, orbiting planets, and the motion of every spacecraft humanity has launched. We do not impose our will on gravity, but learn to work within its framework, guiding our machines along paths it permits. The closer we examine these paths, the more we see gravity not just as a barrier, but as a guide. When a spacecraft leaves Earth orbit and transitions into interplanetary space, it does not escape gravity, but enters a broader domain where gravity from multiple bodies shapes its journey. In this environment, understanding becomes as important as propulsion. Without knowledge of how gravitational forces combine and compete, no mission could reach its target. This final segment of the chapter draws together the truths revealed since the first moment rockets attempted to rise from Earth. Gravity sets the energy required to begin the journey, defines the motion needed to remain in orbit, and governs the routes available to travel beyond our planet. Every burn, every maneuver, and every moment of flight is a response to the invisible contours shaped by mass. The spacecraft that slips away from Earth's influence does so not by overpowering gravity, but by navigating its geometry with precision. As we prepare to explore the deeper reaches of the solar system, this understanding becomes even more essential. The next chapter begins at the heart of this challenge, where remaining aloft in orbit becomes a matter of mathematical clarity and continual partnership with the forces that rule our motion. Before we move deeper, consider this. What does it truly mean to float above a world that never stops pulling you downward? How can a spacecraft fall forever without ever reaching the ground? And if gravity never releases its grip, then what hidden balance keeps astronauts suspended in a state where every object drifts as though mass has forgotten its own weight? The answers are not tricks of perception, but consequences of motion itself, shaped by laws that have guided planets for billions of years. Orbit is not escape. Orbit is surrender to a different kind of falling, one where the ground curves away faster than you can descend. To understand this strange equilibrium, imagine Earth as a vast sphere wrapped in invisible lines that represent the curvature of space around it. Every object near the planet moves within this curved environment, whether it is tethered to the ground or drifting far above the clouds. When a spacecraft reaches low Earth orbit, it has already met one of gravity's most demanding conditions. It has gained enough horizontal velocity to slip into a perpetual fall. The spacecraft moves forward so quickly that as gravity pulls it downward, the surface of Earth curves away beneath it at precisely the same rate. This delicate dance between motion and attraction creates the sensation of weightlessness experienced by astronauts, even though gravity at that altitude remains almost as strong as it is on the ground. The foundation of orbital motion lies in the balance between centripetal acceleration and the spacecraft's sideways speed. If the spacecraft moves too slowly, gravity draws it inward until atmospheric drag tears it apart. If it moves too quickly, its path widens into an ellipse or escapes entirely. The required speed for low Earth orbit is roughly 7 km per second, a value dictated by Earth's mass and radius. This figure does not arise from engineering preference, but from the universal law that Newton defined, a law confirmed by centuries of observation and countless satellite measurements. Every object that orbits Earth, from small CubeSats to the International Space Station, traces its path according to this same principle. Inside the station, astronauts feel as though gravity has vanished, yet their bodies remain under nearly the full influence of Earth's pull. Their apparent weightlessness comes from freefall, the same state a skydiver experiences before air resistance builds into a cushion. The difference is that the station moves forward so quickly that it keeps missing the planet. This continuous fall creates an environment where fluids redistribute. Bones lose minerals, muscles weaken, and experiments behave in ways impossible on Earth. The strange grace of objects drifting through the station is a result of physics unfolding exactly as predicted, not the absence of gravity, but the absence of resistance to its pull. Although orbit may look serene, it is a fragile equilibrium. Earth's atmosphere, even at altitudes of several hundred kilometers, extends outward as a faint and ever-shifting veil. When solar activity heats this upper layer, it expands, increasing drag on objects in orbit. The International Space Station feels this effect regularly. Without periodic reboost maneuvers, its orbit would decay, drawing it closer to the denser atmosphere where drag grows rapidly until re-entry becomes inevitable. These reboosts add small increments of velocity, restoring the balance between sideways speed and gravitational descent. Every adjustment reflects the constant negotiation between motion and drag, a negotiation that never ends for a spacecraft circling Earth. Different missions require different orbital regimes, each chosen to meet specific scientific or operational needs. Weather satellites monitor the planet from geostationary orbit, hovering above a single point on the equator at an altitude of about 36,000 kilometers. From this distance, they circle Earth once per day, matching the rotation of the planet so precisely that they appear motionless in the sky. Navigational satellites used for timing and positioning occupy medium Earth orbit, where their altitude allows wide coverage while maintaining consistent signal timing. Earth observation satellites, meanwhile, often follow sun-synchronous paths, passing over the poles while maintaining a consistent angle relative to the sun. This configuration ensures steady lighting conditions for imaging, a critical factor for climate monitoring and land use studies. Despite their varied purposes, all these orbits rely on the same mathematical structure. Shape, orientation, and altitude govern how a spacecraft behaves over time. Elliptical orbits stretch farther on one side than the other, causing changes in velocity as the spacecraft moves closer or farther from Earth. Circular orbits maintain constant altitude, simplifying mission planning. Inclination determines how a spacecraft's path aligns with Earth's rotation, a factor that affects launch trajectories and fuel requirements. These elements, known as orbital parameters, define the motion of satellites with such precision that their positions can be predicted months or years in advance. Yet orbits are never entirely stable. Small influences, from atmospheric drag to gravitational tugs of the Moon and Sun, produce slow drifts. Engineers monitor these drifts with remarkable accuracy, using tracking stations and onboard instruments to calculate future positions and plan corrective maneuvers. Even the most stable geostationary satellites require occasional nudges to maintain their place above the equator. Without these adjustments, they would slowly wander, falling out of alignment with the terrestrial antennas that depend on them. Orbit is a triumph of physics, engineering, and patience, but it is not the final destination for most exploration. It is a staging ground, a place where spacecraft gather momentum before venturing outward. And once a spacecraft leaves this fragile yet well-understood environment, it must enter the broader gravitational network that binds the solar system together. There, beyond the comfort of predictable low Earth motion, lies a realm where gravitational forces from planets and the Sun shape every possible path. The next chapter begins in that vast network, where navigation becomes a dialogue with multiple worlds rather than one. The moment a spacecraft leaves the familiar stability of low Earth orbit and begins adjusting its path, the underlying mathematics that govern its movement become even more essential. In orbit, motion depends on a careful balance between speed and gravitational pull. But shifting from one orbit to another requires altering that balance in precise and deliberate ways. When engineers speak of adjusting a trajectory, they are really speaking about changing the spacecraft's velocity vector, a subtle modification that shapes the curve it will follow through space. Even a small change in speed or direction can reshape the entire path, raising or lowering altitude, tilting the orbital plane, or altering the shape of an ellipse. These changes demand energy, and energy in spaceflight always traces back to the propellant a spacecraft carries. One of the most efficient ways to change orbits is through what is known as a transfer maneuver. The most common of these is the Hohmann transfer, a method that uses two burns to shift a spacecraft between circular orbits of different radii. The first burn increases or decreases the spacecraft's speed, placing it into an elliptical orbit that intersects the target altitude. The second burn, performed at the opposite point of that ellipse, circularizes the orbit. This method minimizes fuel use while achieving the required change in altitude. Its effectiveness arises not from engineering intuition, but from the underlying mathematics of orbital energy, which dictate that raising a spacecraft's altitude requires increasing its kinetic energy in just the right amount. The Hohmann transfer is elegant because it aligns perfectly with these mathematical constraints. More complex maneuvers arise when a spacecraft must change its inclination, the tilt of its orbit relative to Earth's equator. Inclination changes are costly in terms of fuel because they require altering the direction of motion rather than its speed alone. If a rocket launches directly into the proper inclination, these expensive adjustments can be avoided. This is why launch sites are chosen carefully. Cape Canaveral allows launches into low inclination orbits that align with Earth's rotation, while sites like Vandenberg Air Force Base enable launches into polar orbits. Each location serves as a gateway to specific orbital pathways, reducing the need for large inclination burns once the spacecraft is aloft. As satellites operate in these orbits, they continually interact with a gravitational environment, richer than it first appears. Earth's mass is not distributed with perfect symmetry. Slight bulges, variations in density, and surface features create small irregularities in the gravitational field. These irregularities cause orbits to precess, meaning their orientation slowly shifts over time. Mission designers account for these effects by choosing orbital parameters that naturally exploit or counter these gravitational quirks. Sun-synchronous orbits are a striking example. Their precession rate matches Earth's motion around the Sun, ensuring that a satellite crosses each point on the planet at the same local time each day. This synchronization is not forced through constant correction, but arises from a deliberate choice of altitude and inclination that allows Earth's gravitational irregularities to do the work. Engineers have also learned to use atmospheric drag to shape orbits when fuel is limited. By lowering a spacecraft into slightly denser regions of the upper atmosphere, drag can help reduce speed and shrink the orbit. Some satellites use deployable surfaces to increase this effect, hastening orbital decay when their missions end. This technique allows deorbiting without large fuel expenses, reducing the accumulation of debris that threatens other spacecraft. The careful use of drag shows that even the faintest influences can be valuable tools when understood fully. Throughout all of these processes, navigation depends on measurements of extraordinary precision. Tracking stations scattered across the globe monitor spacecraft positions by analyzing radio signals that travel between Earth and the orbiting vehicle. The time it takes for a signal to travel, combined with the Doppler shift in frequency caused by relative motion, reveals the spacecraft's speed and distance. These measurements allow mission controllers to predict future positions with remarkable accuracy. Even slight discrepancies in timing or signal strength become clues that help refine orbital models. The spacecraft itself often carries star trackers, gyroscopes, and accelerometers, instruments that work together to determine orientation and motion with exquisite detail. The combination of ground-based tracking and onboard sensing creates a portrait of motion that allows for prediction, correction, and long-term planning. The precision required becomes even more apparent when spacecraft interact with one another in orbit. Docking maneuvers, such as those performed by cargo vehicles approaching the International Space Station, depend on synchronization measured in centimeters and fractions of a second. The visiting spacecraft must match speed and trajectory with the station, approaching slowly enough to ensure control, yet quickly enough to maintain stability. These maneuvers reflect not just engineering expertise, but a deep understanding of how objects move in microgravity, where small forces produce slow but inevitable changes in motion. Despite the complexity of orbital mechanics, the principles that govern them remain consistent. Gravity pulls, motion curves. Energy determines altitude. Direction shapes trajectory. These truths apply equally to satellites circling a few hundred kilometers above Earth and to spacecraft preparing for destinations far beyond. And once an object leaves Earth's gravitational dominance, the same principles continue to guide it, though now influenced by multiple bodies rather than one. The spacecraft becomes part of a larger gravitational environment, one where its path must account for the influence of the Sun, the planets, and even the motion of the solar system itself. As we leave the intricacies of Earth orbit behind, the next stage of exploration begins to take shape. Navigating the solar system requires understanding how gravity can be both a barrier and a tool, how momentum can be redirected across immense distances, and how timing becomes as important as thrust. The next part of this chapter draws us closer to that larger stage, where interplanetary pathways unfold through a combination of physics, precision, and the silent guidance of gravitational wells spread across the solar system. The transition from orbit to interplanetary space marks a shift not only in distance, but in the complexity of the gravitational environment a spacecraft must navigate. While motion around Earth depends on a single dominant mass, the broader solar system is a tapestry of intersecting influences. Each planet, moon, and even the Sun itself carves a gravitational well into space-time, shaping the routes a spacecraft may follow. In this realm, precision becomes more than a tool for efficiency. It becomes the only means of ensuring that a trajectory aligns with the timing and geometry required for a mission to succeed. Every second of thrust and every fraction of a degree in orientation has consequences that unfold across millions of kilometers. To leave Earth's gravity behind, a spacecraft must add energy at just the right moment in its orbit. This maneuver places it on what is known as an escape trajectory, a path that no longer loops around Earth but stretches outward, falling instead toward the Sun in a new pattern. Yet even this path is not chosen freely. Earth continues to move in its own orbit at roughly 30 km per second, carrying the departing spacecraft along with it. As a result, the spacecraft begins its interplanetary journey already endowed with Earth's own motion. Engineers factor this inherited momentum into their calculations, using it to shape the craft's route toward its destination. This process reflects a deeper truth about spaceflight. No object moves independently. Every journey begins with the motion of the world it leaves behind. Once a spacecraft settles into its solar orbit, guiding it toward another planet becomes a matter of matching not only distance but timing. The target planet must be in the correct position when the spacecraft arrives, requirement that often demands months or years of travel. Mission planners use detailed models of planetary motion, refined over centuries, to determine the launch window for each mission. If the spacecraft leaves too early or too late, the planet will not be there to meet it, and the mission will fail long before it encounters any scientific instrument or landing system. This exquisite timing is one of the most demanding aspects of interplanetary navigation, a challenge that cannot be solved through brute force or improvisation. It relies solely on the accurate application of celestial mechanics. One of the most powerful tools available to mission designers is the gravity assist, a maneuver that uses the motion and gravitational pull of a planet to increase or redirect a spacecraft's velocity. As the spacecraft approaches the planet, it falls into the planet's gravitational well, accelerating as it descends. When it swings past the planet and climbs back out, the energy exchange between the planet's motion and the craft's trajectory can add or subtract speed. This process does not violate any conservation laws. Instead, it draws from the immense momentum of the planet itself, allowing the spacecraft to change its path without expending large amounts of propellant. Missions like Voyager, Cassini, and Galileo used sequences of gravity assists to reach their distant targets, leveraging the predictable dance of planets around the Sun to reshape their journeys. Although gravity assists are powerful, they require exacting alignment. A small error in the spacecraft's approach angle can produce a very different outcome, altering the trajectory in ways that become more pronounced over time. Engineers closely monitor the craft's position and velocity during these encounters, adjusting its path through fine bursts of thrust to ensure it meets the planet at the correct point. These adjustments are often planned weeks or months in advance, based on data from deep space tracking networks that measure the craft's motion with extraordinary sensitivity. The success of these maneuvers stands as a testament to the precision that modern spaceflight demands. The deeper a spacecraft travels into the solar system, the more subtle the gravitational interactions become. The pull of the Sun dominates near Earth, but gradually yields to the influences of giant planets such as Jupiter and Saturn, whose immense masses reshape nearby space. A probe nearing Jupiter experiences a dramatic shift in its trajectory as the planet's gravity draws it inward. Navigating this environment requires detailed models of the planet's mass distribution, including the contributions of its many moons. Even small irregularities in the gravitational field can steer the spacecraft in unexpected directions, if not accounted for properly. Mission designers study each giant planet carefully, using data from previous missions to refine their navigation models. As a spacecraft moves farther outward, its signals weaken, spreading across the vast distances until they reach Earth as faint whispers detectable only by the most sensitive radio receivers. The Deep Space Network, a system of powerful antennas positioned around the globe, listens for these signals, measuring their travel time and frequency shifts to determine the craft's location. These measurements feed into navigation models that guide future trajectory adjustments. Every correction burn, no matter how small, reflects the constant effort required to keep a mission on course in a gravitational landscape that spans billions of kilometers. Despite the immense distances and the complexity of the forces at play, interplanetary navigation remains an extension of the same principles that shape motion in low Earth orbit. Gravity still pulls, momentum still carries, timing and geometry still rule. The difference lies in scale and sensitivity. Where orbital maneuvers unfold over minutes or hours, interplanetary trajectories unfold over months or years. Where a small error in low orbit may lead to a shift of a few kilometers, the same error in deep space can grow into a gap of millions. Precision is not merely advisable, it is essential. As this chapter draws to a close, the path ahead becomes clearer. Remaining aloft in orbit and navigating the solar system share the same foundation. Both require a profound understanding of how gravity shapes motion. Both demand careful planning and constant attention. And both reveal that space travel is not an act of escaping gravity, but an act of learning to move within its contours. The next chapter will explore how these contours guide spacecraft through the solar system, where gravity assists and transfer orbits transform the silent pull of planets into the means of reaching worlds far beyond our own. Before we begin this next journey, consider a question that hides beneath every successful mission ever sent beyond Earth. What if the vast distances between planets are not empty stretches to be conquered, but pathways carved by gravity itself, routes that have existed long before humanity learned to ride them? What if the solar system is not a void to cross, but a network of invisible currents, each shaped by the pull of worlds drifting through space-time? And if momentum is the only currency that allows a spacecraft to move along these currents, then what secrets lie in the timing, the geometry, and the silent exchanges of energy that guide probes toward destinations millions or even billions of kilometers away? The moment a spacecraft breaks free from Earth orbit and settles into a path around the Sun, it enters a realm where the rules grow both simpler and more profound. In this environment, gravity becomes a sculptor that shapes motion on grand scales, curving the trajectories of planets, comets, and spacecraft alike. The spacecraft does not wander freely, but follows a trajectory determined by its velocity and the gravitational pull of the Sun. This path, though shaped by ancient laws, can be redirected through carefully timed maneuvers that take advantage of the gravitational wells carved by other planets. To travel from one world to another, engineers design these trajectories with extraordinary precision, guided by mathematical principles that have evolved from centuries of celestial observation. One of the most elegant concepts in interplanetary travel is the Hohmann transfer orbit, a method that uses minimal energy to shift a spacecraft from one circular orbit around the Sun to another. This maneuver begins with a burn that increases or decreases the spacecraft's velocity, placing it onto an elliptical path whose aphelion or perihelion touches the orbit of the target planet. If the timing is correct, the spacecraft arrives at the intersection point just as the planet reaches the same location. A second burn then adjusts the spacecraft's speed to match the new orbit. This process may seem straightforward, but its success hinges on the precise alignment of two bodies moving continuously through space, each following its own elliptical route around the Sun. The geometry of the solar system dictates when such transfers are possible, creating launch windows that open and close predictably over time. Yet the Hohmann transfer is only the beginning. Many missions require trajectories that conserve even more energy or reach destinations far beyond the inner planets. For these journeys, mission designers rely on the gravity assist, a maneuver that uses a planet's motion and gravitational pull to alter a spacecraft's trajectory. When a spacecraft approaches a planet, it falls into the planet's gravitational well, accelerating as it descends. As it swings past and climbs back out, the planet's motion imparts a small but significant change in the spacecraft's velocity. The direction and magnitude of this change depend on how the spacecraft approaches the planet, allowing mission planners to craft intricate sequences of assists that reshape the spacecraft's journey across the solar system. The Voyager missions offer a stunning example of this technique. Launched in the late 1970s, Voyager 1 and Voyager 2 used a rare planetary alignment to visit multiple worlds in succession. Each planet they encountered acted as a stepping stone, redirecting their trajectories and accelerating them toward the next destination. The gravity assists from Jupiter and Saturn allowed the probes to achieve speeds that carried them onward to Uranus, Neptune, and eventually toward interstellar space. These missions demonstrated that with the right alignment and trajectory, gravity itself becomes a tool for exploration, enabling spacecraft to reach distances far beyond the capability of their engines alone. The Cassini mission to Saturn also relied on a sequence of gravity assists, using flybys of Venus, Earth, and Jupiter to build the velocity needed for its journey. Each encounter required meticulous planning, with precise calculations ensuring that the spacecraft passed through a narrow corridor of space at exactly the right moment. Even a small deviation could have altered the timing of subsequent encounters, jeopardizing the mission's arrival at Saturn years later. This sensitivity to initial conditions reflects the nature of interplanetary motion. Small errors grow over time, especially over distances measured in hundreds of millions of kilometers. Navigating this vast environment demands not only precise modeling of gravity, but the ability to monitor and correct the spacecraft's path long after it leaves Earth behind. Deep space tracking networks, such as NASA's Deep Space Network, play a vital role in this process. By measuring the time it takes for radio signals to travel between Earth and the spacecraft, and by analyzing the changes in signal frequency caused by relative motion, engineers can determine the spacecraft's velocity and position with extraordinary accuracy. These measurements feed into navigation models that predict the spacecraft's future trajectory and guide the timing of correction burns. Even the slightest adjustment, applied at the right moment, can shift the spacecraft's arrival point by thousands of kilometers, ensuring that it meets its target planet rather than missing it entirely. While gravity assists harness the pull of planets to redirect motion, other maneuvers rely on the spacecraft's own propulsion systems. Small burns performed during interplanetary crews fine-tune the trajectory, compensating for uncertainties in initial launch conditions, gravitational influences from smaller bodies, and minute perturbations that accumulate over time. These course correction maneuvers are a normal part of deep space navigation, each one narrowing the corridor through which the spacecraft must pass to achieve success. The farther a spacecraft travels, the more important these corrections become, as tiny deviations evolve into significant differences over long distances. Interplanetary navigation also requires understanding the gravitational interactions of multiple bodies simultaneously. The patched conic approximation, a widely used method in mission planning, divides the spacecraft's journey into segments dominated by the gravity of a single body. Within each segment, motion is calculated according to that body's gravitational influence. As the spacecraft transitions from one region to another, the calculations are updated to reflect the new dominant mass. This approach simplifies the complex problem of multibody motion while producing results accurate enough for mission design. Through all of these methods, one truth remains clear. Traveling through the solar system is not a matter of overpowering gravity, but of cooperating with it. Each maneuver, whether a gentle burn or a sweeping gravity assist, reflects the natural structure of space-time, shaped by the mass of planets and the energy of motion. The spacecraft does not fight these forces. It joins them, weaving through a gravitational landscape that has existed since the solar system formed. This first part of the chapter has laid the foundation for understanding how missions navigate between worlds. The next part will explore the deeper physics behind momentum exchange, trajectory shaping, and the precise calculations that make interplanetary exploration possible. Once a spacecraft commits to its interplanetary path, every moment that follows becomes an unfolding conversation between momentum and gravity, a dialogue written across distances so immense that even the smallest influence echoes outward for millions of kilometers. The spacecraft carries with it the velocity imparted by its launch and the additional boosts from its gravity assists, yet these are only the starting notes in a long and intricate symphony of motion. Each planet it encounters bends its path with a force that grows stronger as the spacecraft approaches, drawing it inward in a smooth, accelerating curve that reflects the shape of the planet's gravitational well. This motion is not random. It is predictable with such precision that mission designers can trace the craft's future location decades in advance, provided its current trajectory is known with enough accuracy. In this vast space, momentum becomes both a resource and a constraint. The conservation of momentum governs every change in motion, ensuring that no acceleration occurs without an exchange of energy or the influence of a gravitational pull. When a spacecraft swings past a planet during a gravity assist, it trades a tiny portion of the planet's orbital momentum for a change in its own velocity. The planet loses an imperceptibly small amount of energy, but the spacecraft gains a measurable boost that alters its path through the solar system. This exchange works because both bodies are part of the same celestial dance, orbiting the Sun together in a fluid system governed by the same laws. The spacecraft simply shifts from one gravitational partnership to another, using the planet's motion to redefine its own. Consider the case of Voyager 2, which approached Jupiter at just the right angle to bend its trajectory towards Saturn. Without that perfectly timed encounter, the spacecraft would never have reached Uranus or Neptune, nor would it have gained the velocity needed to escape the solar system entirely. The trajectory depended on calculations that mapped Jupiter's gravitational field with extraordinary detail, incorporating not only the planet's mass, but also the small contributions from its many moons. As Voyager 2 flew through this region, it accelerated rapidly, gaining the energy required to continue outward. The deflection of its path was not magical or mysterious. It was the result of precise geometry, the relative motions of two bodies meeting in a gravitational embrace that reshaped the spacecraft's future. The Cassini mission followed a similar pattern. To reach Saturn with the limited fuel available, the spacecraft relied on a complex sequence of flybys. It first encountered Venus, then Earth, then Venus again, each encounter adding to its velocity. These assists allowed Cassini to reach Saturn without requiring an impossibly large launch vehicle. The final leg of its journey depended on a gravity assist at Jupiter, which altered its trajectory and provided the additional speed necessary to enter orbit around Saturn years later. The mission designers crafted this pathway with an understanding of how planetary motion creates opportunities that come and go. Cassini launched at a time when these alignments formed a workable chain, an arrangement that would not recur for many years. As a spacecraft continues deeper into the solar system, the influence of gravity grows more complex. The gravitational pull of the Sun remains dominant, but the giant planets create significant perturbations. Jupiter, with its immense mass, shapes the trajectories of comets, asteroids, and spacecraft that pass near its orbit. Even from great distances, its gravitational field can alter the motion of smaller bodies. Saturn exerts a lesser but still significant influence, particularly on trajectories that pass near the outer planets. Navigating this environment requires models that incorporate not only the masses of planets, but their orbital positions, rotations, and even small irregularities in their internal mass distributions. These models are refined by data gathered over decades of observation. Radar mapping, spacecraft flybys, and long-term gravitational studies have revealed that planets are not perfect spheres with uniform mass. Jupiter, for instance, exhibits subtle variations caused by its turbulent atmosphere and deep interior structure. These variations create tiny deviations in its gravitational pull, deviations that can alter the path of a spacecraft during a close approach. Understanding these nuances allows mission designers to predict how a craft will move as it swings past the planet, ensuring that it emerges on the correct trajectory. The patched conic approximation remains one of the most reliable methods for planning interplanetary trajectories. In this approach, the solar system is divided into regions dominated by different gravitational sources. When the spacecraft is far from planets, the Sun's gravity governs its motion. As it approaches a planet, the calculations shift to reflect the gravitational dominance of that world. After the flyby, the calculations switch back to the Sun-centered frame. This method simplifies the complex multi-body interactions of the solar system, yet produces results of remarkable accuracy. It allows engineers to design missions that hop from one gravitational well to another, linking planetary assists into a coherent trajectory. Even with these tools, no mission can rely solely on predictions made at launch. The spacecraft must be monitored continuously, its position tracked through the signals it sends back to Earth. These signals travel across millions or billions of kilometers, spreading out as they move, weakening until they are little more than delicate threads of radio waves. The Deep Space Network listens for these threads with antennas that span continents, comparing the timing and frequency of the signals to determine the spacecraft's location. From these measurements, engineers calculate when and how to perform course corrections. These adjustments, though small, are crucial. A brief burn lasting only seconds can shift the spacecraft's arrival point by thousands of kilometers after months of travel. Interplanetary exploration demands an extraordinary partnership between prediction and correction. Engineers must anticipate the effects of gravity, solar radiation, and the motion of celestial bodies with great precision. They must then respond to real-time data, guiding the spacecraft through the corridors of space that lead to its destination. The process is both analytical and intuitive, blending the cold beauty of mathematics with the practical challenges of maintaining a fragile machine far from home. Through all of this, the spacecraft remains a silent traveler, drifting along the pathways carved by gravity, shaped by forces that have acted for billions of years. It does not choose its route. It follows the geometry of the solar system, moving where momentum and gravity allow. And yet within that constraint lies a freedom born from understanding. Humanity has learned to navigate these pathways not by overpowering nature, but by listening to it, by reading the subtle patterns of mass and motion that bind the planets together. The next part of the chapter will explore how these pathways become the framework for mission design, showing how geometry, timing, and the exchange of momentum determine which destinations are possible and how spacecraft reach them across the vast distances that separate worlds. The pathways that guide spacecraft through the solar system are not mere lines drawn across empty space. They are the natural routes carved by gravity, the quiet architecture of motion that has governed planets for billions of years. When mission designers plan an interplanetary journey, they do not force a spacecraft along an arbitrary path. Instead, they search for the trajectory that nature already provides, the one that requires the least energy, aligns with planetary motions, and cooperates with the gravitational wells scattered across the solar system. These routes can be predicted with astonishing precision, yet they remain profoundly shaped by timing. A launch delayed by even a few weeks may alter the entire sequence of planetary alignments, closing off opportunities that will not return for years or decades. The concept of a launch window arises from this dependence on timing. For a spacecraft to reach another planet using a Hohmann transfer or more complex trajectory, Earth and the target planet must be positioned so that the spacecraft will arrive at the same point in its orbit as the destination. The geometry of this alignment changes constantly as the planets move around the Sun at different speeds. For Mars missions, launch windows open roughly every 26 months, when Earth catches up to Mars in a favorable configuration. For outer planets, the intervals grow longer. The remarkable Grand Tour trajectory that enabled Voyager to visit multiple giant planets occurred because Jupiter, Saturn, Uranus, and Neptune aligned in a way that would not recur for more than a century. Without that rare alignment, the Voyager missions could not have followed their historic paths. Even when the planets align, the spacecraft must still be guided with exquisite control. The initial burn that sends it from low Earth orbit onto an interplanetary trajectory must be timed to the second and angled with remarkable precision. A small deviation at this stage grows steadily over the months or years of travel. Mission designers compensate for this growth with trajectory correction maneuvers, small adjustments that nudge the spacecraft back toward the narrow corridor required for arrival. These corrections are based on tracking data sent from Earth, where the Deep Space Network evaluates each signal for clues about the craft's position and velocity. Engineers study these clues carefully, interpreting tiny frequency shifts that reveal the spacecraft's drifting motion relative to Earth. The farther the spacecraft travels, the more sensitive the navigation becomes. A correction burn lasting only a fraction of a minute may determine whether the spacecraft reaches its target planet or misses entirely, traveling instead into a different region of the solar system. This sensitivity emerges from the basic geometry of the situation. The spacecraft moves along a vast elliptical path shaped by gravity, and even tiny changes at early stages produce amplified effects later. This amplification is not a flaw in the system, but a natural consequence of motion through the wide arcs of interplanetary space. The key to successful navigation lies in continuous observation and timely correction. Gravity assists remain among the most powerful tools for reshaping these paths. When a spacecraft approaches a planet, the gravitational pull draws it inward, accelerating the craft as it descends into the planet's well. As it swings past the planet and rises out again, the motion of the planet along its own orbit imparts a shift to the spacecraft's momentum. This transfer of energy does not violate any physical law. It simply reflects the conservation of momentum in a many-body system. The planet loses an imperceptibly small amount of its orbital energy, but the spacecraft gains speed or changes direction in a way that would otherwise require large amounts of propellant. The angle of approach determines whether the spacecraft leaves the encounter with increased velocity, decreased velocity, or a new direction altogether. Missions often rely on multiple gravity assists to reach their final destinations. The Galileo mission used flybys of Venus and Earth to gather enough speed to reach Jupiter. The Juno mission relied on an Earth flyby to gain the energy required to enter Jupiter's orbit. The New Horizons spacecraft used a gravity assist at Jupiter to accelerate toward Pluto, cutting years off its journey. Each of these missions demonstrates how gravity can serve as a pathway rather than a barrier, offering energy and direction to spacecraft that understand its patterns. Even the concept of a low-energy transfer, where a spacecraft drifts slowly through regions of balanced gravitational influence, reflects the natural structure of the solar system. These trajectories, sometimes called weak stability boundary transfers, take advantage of areas where gravitational forces from different bodies nearly cancel. Moving through these areas requires little energy but demands great patience and precision. The Genesis mission used such dynamics to collect solar wind samples, drifting along pathways defined by the delicate interplay of Earth and solar gravity. These routes reveal that even subtle variations in gravitational influence can be used for exploration, provided the models are accurate and the timing is correct. Underlying all of these techniques is a deep trust in physics. Every maneuver, whether powered by a rocket engine or shaped by planetary gravity, depends on equations that describe how objects move under the influence of mass. These equations, refined over centuries, allow mission designers to predict trajectories with extraordinary reliability. Yet prediction alone is not enough. The spacecraft must respond to those predictions with real motion, firing its thrusters or adjusting its orientation to remain on course. The partnership between mathematics and machinery becomes the lifeline that carries each mission from its launch to its distant target. As this chapter concludes, a clearer picture emerges of how we traverse the solar system. We do not simply point a spacecraft toward a planet and hope for the best. We design journeys that respect the natural rhythms of planetary motion, the curvature of space-time, and the exchanges of momentum that occur when bodies interact. Gravity is not an obstacle to be overcome, but a structure to be understood, a framework within which all motion unfolds. The next chapter will shift from the pathways that carry spacecraft through space to the engines and technologies that give them the ability to follow those paths, revealing the physics of propulsion that underlies every voyage beyond Earth. Before we ignite the engines that carry spacecraft across the solar system, pause for a moment and consider a question that lies at the heart of every mission humanity has ever launched. What does it truly mean to push against the emptiness of space, where there is no air to grip and no ground to press against? How can a machine create motion in a realm where direction and resistance seem to vanish? And if every journey beyond Earth requires not just momentum, but a way to change that momentum, then what hidden limits has physics placed on the engines we build? And what innovations allow us to stretch those limits while remaining bound to the laws of nature? From the earliest attempts to rise above the ground, humans learned that propulsion requires expelling something backward to move forward. This principle arises from the conservation of momentum, a law that emerges from the symmetry of space itself. A rocket engine does not push against the air or the ground. It pushes against its own exhaust, flinging mass outward at high speed so that the rocket accelerates in the opposite direction. This fundamental truth shapes every engine used in spaceflight, from the simplest solid rocket boosters to the most sophisticated ion thrusters. Nothing moves without exchanging momentum, and nothing accelerates without expelling energy and mass. Chemical propulsion, the oldest and most widely used form of rocket power, relies on rapid chemical reactions that convert stored energy into hot gases. These gases expand and rush through a nozzle, producing thrust as they leave the engine. The power of chemical engines lies in the amount of energy released per unit of mass, and the speed at which the exhaust escapes. The specific impulse, a measure of how efficiently an engine produces thrust, depends on these factors. Engines that burn liquid hydrogen and liquid oxygen achieve some of the highest specific impulse values among chemical systems because the reaction produces extremely hot, lightweight exhaust that can accelerate quickly through the nozzle. Yet even the most powerful chemical engines face limits set by physics. The Tsiolkovsky rocket equation describes how the change in velocity a rocket can achieve depends on its exhaust velocity and the ratio of its initial mass to its final mass. This equation reveals a harsh reality. To increase a rocket's speed, one must increase the mass of propellant it carries, but doing so also increases the mass that must be accelerated. The result is an exponential relationship where achieving even modest increases in velocity requires disproportionately large amounts of fuel. This limitation explains why rockets appear so massive, yet carry relatively small payloads. Most of their mass at launch consists of propellant needed simply to lift the rocket itself and escape Earth's gravitational pull. The challenge becomes even greater when missions require acceleration after leaving Earth orbit. Chemical engines can provide large bursts of thrust, making them ideal for launch and major course changes, but their efficiency limits make them less suitable for long-duration missions that require sustained propulsion. Engineers therefore explore alternatives that trade high thrust for high efficiency, allowing spacecraft to add velocity gradually over long periods. Electric propulsion systems, such as ion thrusters and Hall thrusters, exemplify this approach. Instead of relying on chemical reactions, these engines use electric fields to accelerate ions to extremely high speeds. The resulting exhaust velocity far exceeds that of chemical systems, giving electric engines much higher specific impulse. The drawback of electric propulsion lies in its relatively low thrust. Ion engines produce only small amounts of force, often comparable to the weight of a sheet of paper resting in one's hand. But in the frictionless environment of space, even such gentle thrust accumulates over time. The Deep Space One mission and the Dawn spacecraft demonstrated the power of this method, gradually reshaping their orbits through continuous, efficient use of ion propulsion. Dawn, in particular, used its ion engines to visit both Vesta and Ceres, becoming the first spacecraft to orbit two celestial bodies beyond Earth. Such achievements highlight the value of propulsion systems that prioritize efficiency over raw strength. Solar sails offer yet another method of propulsion, one that requires no propellant at all. Instead of expelling mass, these sails capture momentum from sunlight itself. Photons, though massless, carry energy and momentum. When they strike a reflective surface, they transfer a tiny amount of that momentum, exerting a gentle pressure. A large, ultra-lightweight sail can harness this pressure, accelerating slowly but continuously as long as it remains illuminated. The Icaros mission from the Japan Aerospace Exploration Agency demonstrated this technology in interplanetary space, proving that sunlight can indeed propel a spacecraft without consuming any fuel. Solar sails operate within the strict boundaries of physics, yet open pathways for missions that require endurance rather than speed. Nuclear thermal propulsion represents another approach, one rooted in decades of research and testing. By heating a propellant such as hydrogen with a nuclear reactor, these engines can produce thrust with higher efficiency than chemical rockets. The high temperatures achieved in such reactors allow the exhaust to reach velocities greater than those produced by typical chemical reactions. Although no nuclear thermal engine has flown in space, ground tests during the 20th century demonstrated significant performance potential. Modern studies continue to evaluate this technology, exploring materials and reactor designs that could make it a viable option for future missions, particularly those requiring rapid travel within the solar system. Despite the diversity of propulsion methods, all of them remain bound to the same fundamental laws. They must conserve momentum, exchange energy, and accelerate mass in ways that comply with the geometry of space-time. None can bypass the limitations imposed by the rocket equation. Engineers therefore design missions around these constraints, choosing propulsion systems that match the goals, distances, and required velocities. Some missions demand high thrust to escape gravity wells. Others rely on slow, steady acceleration to reshape orbits across years. Each choice reflects a balance between efficiency, power, and practicality. As we explore deeper into the solar system, these propulsion technologies form the backbone of every journey. Yet propulsion alone does not determine the possibilities. It must work in concert with gravity, trajectory design, and the evolving architecture of mission planning. Understanding the physics of propulsion reveals the challenges and opportunities that lie ahead, setting the stage for how spacecraft navigate the gravitational landscape of planets and moons. The next part of this chapter will continue this exploration, revealing how engineers push against the limits of physics while ensuring that every mission remains grounded in the laws that govern motion throughout the cosmos. The physics that govern propulsion do not soften as missions grow more ambitious. Instead, they become sharper, more demanding, and more revealing of how tightly engineering must align with the natural limits imposed by the universe. Every spacecraft that leaves Earth carries only a finite amount of propellant and a finite amount of electrical power. These reserves must be used with extraordinary care, because once a spacecraft drifts into deep space, there are no refueling stations, no air to push against, and no hidden source of energy waiting to be harvested. The spacecraft must rely entirely on the engine systems it brought from Earth. Shaped by the unbreakable constraints of the rocket equation and the unforgiving environment of interplanetary space, chemical engines, despite their limitations, remain indispensable for many critical phases of flight. The immense thrust they provide allows a spacecraft to escape Earth's gravitational well, perform rapid course corrections, or execute insertion burns when approaching another planet. The descent to a surface, whether Mars or the Moon, depends heavily on engines capable of quick and precise changes in velocity. These moments demand power rather than endurance, a sudden release of energy that carves a new trajectory in a matter of seconds. But once these intense maneuvers are complete, the spacecraft often transitions to more efficient propulsion methods that extend its reach without exhausting its fuel too quickly. This is where electric propulsion shows its strength. While chemical engines deliver their energy in short bursts, electric engines deliver it slowly, but with remarkable efficiency. Their high specific impulse reflects the incredible speed of their exhaust, which can exceed tens of kilometers per second. Yet the thrust they produce remains gentle, almost imperceptible. If one were to stand beside an ion engine firing in deep space, nothing would shake or roar. There would be no thunder or plume of flame. The engine would simply glow faintly, pushing the craft forward with a force so small that it would take hours or days to notice any change in speed. But that change accumulates. Day by day, month by month, the engine reshapes the craft's path, raising or lowering its orbit, or steering it toward a distant target. The Dawn spacecraft remains one of the clearest demonstrations of this gradual yet transformative propulsion method. By firing its ion engines for long durations, Dawn was able to slip into orbit around Vesta, study the asteroid, then leave its gravitational influence and travel onward to Ceres. No chemical propulsion system could have achieved such a sequence within the constraints of mass and fuel that modern launch vehicles can support. Only the steady precision of electric propulsion made that journey possible. Dawn's motion, tracked and measured across millions of kilometers, became a quiet testimony to the power of sustained, efficient thrust. Other mission concepts looked toward electric propulsion for even more ambitious goals. High-power solar electric propulsion could support cargo missions to Mars, reducing the mass that crewed missions must carry. Advanced ion engines, powered by next-generation solar arrays or nuclear reactors, could reshape outer planet exploration by allowing spacecraft to maneuver more freely among moons or orbital paths. Each technological advancement, however, must respect the underlying physics. Higher exhaust velocities improve efficiency but demand greater electrical power. Generating that power requires solar arrays or reactors capable of delivering energy consistently across vast distances from the Sun. Engineers must weigh these requirements carefully, testing materials and designs that can withstand radiation, micrometeoroids, and the cold of deep space. Solar sails, meanwhile, offer an entirely different vision of propulsion, one free from fuel constraints. These sails unfold like delicate mirrors, catching sunlight across immense surfaces. Each photon that reflects from the sail transfers a minuscule amount of momentum, almost too small to measure in a single instant. Yet over time, this force can accelerate a spacecraft to impressive speeds, limited only by the intensity of sunlight and the sail's durability. Missions such as Icaros have shown that solar sails can operate reliably, adjusting their orientation to maintain thrust or steer along new paths. Unlike engines that must carry propellant, solar sails require only the constant flow of sunlight, making them well suited for long-duration missions where endurance matters more than immediate power. Nuclear thermal propulsion sits between the brute strength of chemical rockets and the efficiency of electric systems. By heating a propellant, such as hydrogen, through a compact nuclear reactor, these engines can produce thrust levels comparable to chemical rockets, but with far greater efficiency. The high temperatures allow the exhaust to exit the nozzle at high speed, raising the specific impulse and reducing the amount of fuel required for major maneuvers. Studies at NASA and the Department of Energy have explored materials capable of withstanding the extreme environment inside these reactors. Although engineering challenges remain, the potential applications include rapid crewed missions to Mars or fast transit to outer planets. Yet nuclear propulsion, like all other methods, is shaped by the same constraints that govern motion across the universe. It cannot bypass the rocket equation. It cannot create momentum from nothing. It can only accelerate mass, exchange energy, and shape motion along trajectories permitted by gravity. Engineers therefore approach nuclear propulsion with the same discipline applied to all spaceflight technologies, ensuring that every claim remains grounded in evidence and every design respects the laws of nature. As the solar system becomes a stage for exploration, propulsion emerges not as a single technology, but as an intricate ecosystem. Chemical engines lift, electric engines refine, solar sails drift, and nuclear concepts promise new capabilities. Together they form a spectrum of options, each suited to a different mission profile. The challenge for engineers is not simply to choose a propulsion system, but to integrate it into a design that harmonizes with trajectory planning, planetary gravity, available energy, and the practical limits of mass. Through this interplay, propulsion becomes a language through which humanity negotiates with the cosmos. Every journey begins with a question: how much energy is required? How much mass must be carried? How can the laws of physics be used to our advantage rather than resisted? These questions shape the architecture of missions, the design of spacecraft, and the future of exploration. And above all, they remind us that every engine, no matter how advanced, remains a student of gravity. The next part of this chapter will explore how these propulsion systems interact with mission design, showing how engineers match engines to destinations and uncover the limits of what physics allows. The architecture of every deep space mission begins with a conversation between ambition and limitation, a discussion shaped by the propulsion system that will carry the spacecraft across millions or billions of kilometers. Engineers must work within the boundaries defined by mass, energy, and the rocket equation, choosing propulsion methods that match the tasks the mission must accomplish. This choice determines not only how the spacecraft will travel, but what scientific instruments it can carry, how long the journey will take, and how much flexibility the mission will have once it reaches its destination. Propulsion is therefore not a mere component, but the backbone of mission planning, a foundation that supports every decision made long before the spacecraft leaves the launch pad. Chemical propulsion dominates the earliest phases of nearly every mission because it alone provides the tremendous thrust required to climb away from Earth's surface. When a rocket rises through the atmosphere, it must overcome gravitational pull and atmospheric pressure, both of which demand enormous amounts of energy delivered quickly and forcefully. The engines burn propellant at astonishing rates, generating thrust measured in millions of newtons during the ascent of heavy launch vehicles. These engines do not aim to be efficient in the long term. Their purpose is urgency. Once the spacecraft reaches orbit, however, the needs shift dramatically. The environment becomes one of silence and vacuum, where a burst of thrust applied for a fraction of a second can alter a trajectory measured in thousands of kilometers. The propulsion system chosen for operations beyond Earth determines how freely a spacecraft can move once in space. If the mission requires only occasional adjustments, as is often the case for distant telescopes or planetary orbiters, small chemical thrusters may suffice. These thrusters fire briefly to correct orientation, refine orbital insertion, or perform minor course adjustments. The amount of fuel they consume is small, but their reliability must be absolute. A single malfunction in a critical moment could jeopardize the mission. When missions require significant maneuvering after launch, electric propulsion becomes a compelling option. Journeys that include multiple orbital adjustments or extended operations near a planetary body benefit from the high efficiency of ion engines, which allow a spacecraft to alter its trajectory without exhausting its propellant reserves prematurely. The Dawn spacecraft demonstrated this advantage brilliantly during its exploration of Vesta and Ceres. To achieve similar feats using chemical propulsion would have demanded propellant masses far beyond the limits of existing launch vehicles. The slow steadiness of electric propulsion, rather than limiting Dawn, expanded its capabilities by granting it the endurance needed to orbit two worlds in succession. Mission designers must therefore weigh the trade-off between thrust and efficiency. Chemical engines offer power, but that power comes at the cost of fuel. Electric engines offer efficiency, but that efficiency comes with low thrust. Solar sails offer propulsion without fuel, but rely on sunlight and require extremely lightweight designs. Nuclear thermal propulsion offers strong thrust and improved efficiency, but introduces engineering complexities related to reactor shielding, material durability, and thermal management. Each option exists within the same physics, yet each bends the constraints in its own way. Factors such as travel time, destination, and mission objectives help determine which propulsion system to use. A crewed mission to Mars, for example, may require faster transit times to reduce exposure to radiation and microgravity. Chemical propulsion combined with nuclear thermal engines could shorten travel durations compared to purely chemical methods. Cargo missions, however, may accept longer travel times, making high-efficiency electric propulsion more suitable. Missions to the outer planets must consider the declining intensity of sunlight, which limits the effectiveness of solar electric engines and solar sails. In such distant regions, nuclear-powered electric thrusters become more practical, relying on radioisotope generators or reactors to supply electrical energy. Even in missions that rely primarily on gravity assists, propulsion remains essential. A spacecraft must often perform burns to refine its approach to a planet, adjust the angle of its flyby, or correct the timing of its trajectory. These small adjustments may be measured in meters per second, yet without them, the carefully planned sequence of planetary encounters could drift out of alignment. The Voyager missions required such fine-tuning during their long journeys, ensuring that their trajectories matched the exact geometry needed to encounter one giant planet after another. The precision demanded in these maneuvers shows that even in a mission largely guided by gravity, propulsion must always remain ready to shape the path. The long-term operation of many spacecraft also depends on propulsion systems for station keeping. Observatories such as the James Webb Space Telescope orbit near gravitationally stable regions, yet these regions are not perfectly balanced. Small disturbances from solar radiation pressure or gravitational irregularities require occasional adjustments to maintain the correct orbit. These adjustments rely on thrusters that fire sparingly but with careful control. The lifespan of such missions often depends directly on how efficiently these adjustments are performed and how much propellant remains. At the core of all propulsion choices lies the enduring presence of physics. No engine can escape the tether of conservation laws. No design can generate motion without exchanging momentum. The question is never how to bypass these limits, but how to work elegantly within them. Engineers study exhaust velocities, mass ratios, energy densities, and mission architectures with the understanding that every calculation reflects the natural order of the universe. The rocket equation does not bend. The laws of thermodynamics do not compromise. The curvature of space-time does not shift to accommodate human preference. Instead, humanity must craft its machines in harmony with the cosmos, shaping missions that use the laws of motion as allies rather than adversaries. As propulsion technologies evolve, they open new possibilities for exploration, yet they do so without altering the foundation that underlies all motion. The future may bring engines that use advanced materials, new forms of energy, or improved efficiency, but each will still speak the language of momentum and gravity. They will still negotiate with the cosmic architecture, seeking the most efficient way to navigate the gravitational wells that fill the solar system. With this understanding, the chapter draws to a close. The engines that lift spacecraft from Earth and carry them across the solar system reflect both the potential and the boundaries of our technological progress. They allow humanity to explore distant worlds, yet remind us that every journey must honor the laws of nature. In the next chapter, the focus will shift from propulsion systems to the gravitational landscape of the solar system itself, where planets and moons carve deep wells that shape the paths every spacecraft must follow. Before we begin charting the deep structure of the solar system, pause and consider something subtle yet profoundly influential. What if every planet, every moon, every asteroid is not merely a sphere floating in space, but a sculptor shaping the very terrain of motion around it? What if the invisible wells carved by their mass determine not only where a spacecraft can go, but how much energy it must surrender or gather to get there? And if these wells form a landscape as real as valleys and mountains on Earth, then what hidden contours lie beneath our journeys between worlds, guiding us long before we ever ignite an engine? Every object with mass shapes the fabric of space-time, creating a gravitational well whose depth depends on the object's mass and size. These wells determine how much energy is needed for a spacecraft to enter orbit, descend to a surface, or escape entirely. Earth's well is deep, demanding enormous amounts of energy for launch and imposing strict requirements for return. The Moon's well is shallower, allowing smaller landers to reach its surface with less propellant and enabling easier escape for missions returning home. Mars, positioned between Earth and the gas giants in both distance and gravitational strength, presents a well less forbidding than Earth's, but far more demanding than that of the Moon. Each of these wells becomes a gate through which exploration must pass, shaping both the scale and feasibility of missions. Understanding the architecture of the solar system requires seeing these wells not as isolated depressions, but as a connected landscape. The Sun sits at the center with the deepest well, a vast basin that holds every planet in its grip. The planets orbit within this basin, their own wells superimposed upon the greater curvature imposed by the Sun. A spacecraft, traveling from Earth to Mars, must navigate through this combined structure, moving from the steep descent of Earth's well into the broader curve of solar gravity, then falling gently into Mars's comparatively moderate depression. Each transition requires energy, and each transition demands a trajectory that cooperates with the natural slopes of space-time rather than fighting them. One of the clearest examples of how gravity shapes mission design arises from the concept of escape velocity. This value represents the minimum speed a spacecraft must reach to climb out of a gravitational well without additional propulsion. For Earth, escape velocity is roughly 11 km per second, a speed that reflects the strength of Earth's mass and the closeness of its surface. The Moon requires far less, only about 2 km per second, because its mass is small and its radius modest. Mars falls between these extremes, with an escape velocity near 5 km per second. These differences reveal why missions to the Moon are less energy-intensive than missions to Mars, and why Earth remains the most demanding starting point for any journey. The influence of gravity extends far beyond escape. When a spacecraft approaches a planet, the depth of that planet's well determines how much energy the craft must shed to enter orbit or land on the surface. A spacecraft arriving at Mars must perform a burn or use atmospheric entry techniques to slow enough to be captured. Missions to the Moon must rely entirely on propulsion to brake for landing, because the Moon lacks an atmosphere dense enough to provide aerodynamic deceleration. At Jupiter, the challenge becomes far more extreme. Its deep gravitational well demands immense energy for orbital insertion, a requirement that shaped the design of missions such as Juno. The spacecraft approached Jupiter on a trajectory that allowed it to fire its engine at precisely the right moment, slowing itself into orbit while avoiding excessive exposure to the planet's intense radiation belts. Wells do not act alone. The interplay between them creates points of balance where gravitational forces from two bodies align. These regions, known as Lagrange points, offer locations where a spacecraft can remain in a stable or semi-stable configuration with minimal fuel use. The James Webb Space Telescope occupies one such region, the second Lagrange point of the Earth-Sun system, where it maintains its position through small station-keeping burns. Other missions, such as the Solar and Heliospheric Observatory, operate at the first Lagrange point, positioned between Earth and the Sun. These points serve as harbors within the gravitational landscape, places where spacecraft can observe, monitor, or communicate with unparalleled efficiency. The gravitational wells of smaller bodies, such as asteroids and comets, present their own challenges. Their wells are so shallow that a spacecraft can descend or ascend with minimal effort, yet the weak gravitational pull complicates surface operations. Rovers on Mars rely on predictable surface weight to gain traction, but on a small asteroid, movement becomes delicate and unpredictable. Missions such as the OSIRIS-REx spacecraft demonstrated how careful navigation is required when interacting with bodies whose gravitational pull is barely measurable. The probe had to approach Bennu with extreme caution, using gentle thruster firings and precise tracking to avoid drifting uncontrollably from the surface. Jupiter's gravitational well, the second deepest in the solar system after the Sun, reveals how profoundly gravity can shape exploration. Any mission approaching the giant planet must account for its massive pull, which accelerates incoming spacecraft to high velocities. These speeds complicate orbital insertion and increase the energy required to slow the spacecraft to a safe path. The gravitational influence of Jupiter extends far beyond its physical size, affecting the motions of its dozens of moons and even shaping the belts of asteroids that orbit nearby. Its presence creates a dynamic environment that has steered comets and small bodies for billions of years, acting as both a shield and a shepherd within the solar system. The concept of gravitational architecture extends beyond simple wells into the subtle structures created by multi-body interactions. When two or more bodies influence an object simultaneously, the result can be a complex network of potential pathways that require precise modeling to predict. Some regions of space form corridors where minimal energy is needed to travel from one gravitational basin to another. These low-energy pathways, revealed through detailed studies of dynamical systems, offer possibilities for missions that prioritize efficiency over speed. A spacecraft traveling along such a path might drift between moons or planetary regions with minimal fuel use, following a route shaped entirely by the natural geometry of the gravitational landscape. This chapter reveals gravity not as a static force, but as a living topography that shapes every movement within the solar system. Each planet and moon contributes to this structure, creating a landscape of wells, slopes, and equilibrium points that spacecraft must navigate with care. Propulsion provides the means, but gravity provides the map. And in the next part of this chapter, the focus will shift to how these wells determine mission planning, orbital insertion strategies, and the delicate maneuvers required to move from one gravitational domain to another. The gravitational landscape of the solar system becomes far more intricate once we move beyond the simplified diagrams that flatten planets into dots and their wells into smooth curves. In reality, each gravitational well possesses subtle contours shaped by mass distribution, rotation, and the interactions of nearby bodies. These contours influence not only how spacecraft enter or leave an orbit, but how they maneuver once inside it. When a spacecraft descends toward a planet, it is not merely falling into a tidy bowl, but into a terrain of invisible ridges and slopes that shape every moment of its motion. Mission planners must understand these nuances long before launch, because they determine the propellant required, the timing of maneuvers, and the amount of freedom available to refine a trajectory along the way. The depth of a gravitational well determines the energy required for orbital insertion, yet the shape of the well dictates how that energy must be delivered. Consider a spacecraft approaching Mars. The planet's modest gravitational field allows atmospheric entry to play a central role in slowing the craft. As the spacecraft plunges into the upper atmosphere, friction converts kinetic energy into heat, shedding enough speed for the craft to transition either into orbit or toward a landing sequence. This process, called aerobraking, when used gradually over multiple orbits, enables missions to conserve fuel by using the atmosphere as a natural brake. The Mars Reconnaissance Orbiter famously used aerobraking for months to reshape its elliptical capture orbit into a stable, low-altitude path, ideal for imaging. Without this technique, the spacecraft would have required an impractically large amount of propellant. The Moon presents a stark contrast. With no atmosphere to speak of, it offers no aerodynamic braking. A spacecraft approaching the lunar surface must rely entirely on engine burns to slow its descent. The Apollo missions performed a sequence of carefully timed maneuvers to ensure that the lunar module descended safely, burning propellant at each stage to counter the pull of lunar gravity. The well may be shallow compared to Earth's, but the absence of air removes a valuable ally, demanding a higher degree of precision in propulsion and guidance. Even small errors in velocity or altitude during descent could mean missing the intended landing site or striking the surface at unsafe speed. Jupiter's gravitational environment further demonstrates how wells shape mission design. A spacecraft approaching the giant planet accelerates rapidly as it falls inward, gaining immense velocity that must be reduced for orbital capture. Chemical engines, despite their limitations, remain essential for such maneuvers because of the sudden deceleration required. The Juno spacecraft executed a dramatic orbit insertion burn upon arriving at Jupiter, firing its main engine for more than half an hour to slow enough for capture. Without that burn, Juno would have sped past Jupiter, carried away by the very gravitational energy it gained during approach. This delicate balance shows how gravity both assists and challenges exploration, offering routes across the solar system while demanding strict adherence to its terms. Beyond planets, gravity wells of moons and smaller bodies create a secondary architecture layered atop the primary wells of their parent planets. Moons such as Europa, Ganymede, and Titan possess enough mass to shape orbits in significant ways, yet their wells remain deeply nested within the larger wells of Jupiter and Saturn. Navigating these layered environments requires understanding the combined influences of multiple bodies. The Galileo and Cassini missions performed repeated flybys of moons, using slight gravitational pulls to adjust their orbits without expending large amounts of fuel. Each close encounter altered the spacecraft's trajectory in subtle ways, allowing mission planners to choreograph sequences that would have been impossible with propulsion alone. These gravitational interactions reveal that motion through the solar system is rarely a straight line. A spacecraft must ascend and descend through wells, cross saddle points, and navigate regions where the pull of two bodies competes. Engineers model these transitions with extraordinary care, using numerical simulations that integrate gravitational effects over long spans of time. The precision required becomes clear when missions target small bodies. Asteroids possess such weak gravity that a spacecraft can drift away with the slightest disturbance. OSIRIS-REx, while sampling material from Bennu, approached the surface at speeds comparable to a slow walking pace. Any faster, and the spacecraft might have rebounded into space. Any slower, and it risked lingering too long in a region where microgravity interactions become unpredictable. Mission planners also consider the gravitational influence of the Sun when designing outer planet missions. As spacecraft journey farther from the Sun, solar gravity remains the dominant force, guiding them through broad arcs that define their long-term trajectories. Even at vast distances, the Sun's gravitational pull dwarfs that of planets until the spacecraft draws close to a giant like Jupiter. This hierarchical structure ensures that motion through the solar system follows predictable layers of influence, each of which must be understood in the context of long-term energy and momentum exchange. Within this gravitational landscape lie the Lagrange points, subtle regions of balance that offer resting places within the flow of space-time. These points emerge from the combined influence of two bodies orbiting one another, such as Earth and the Sun, or Earth and the Moon. At these points, the gravitational pulls and orbital motions align in a way that allows a spacecraft to remain in a stable or semi-stable configuration. The James Webb Space Telescope sits near one of these points, allowing it to maintain a constant orientation relative to Earth and the Sun with minimal fuel consumption. Its successful placement demonstrates the power of understanding gravitational topology, using the landscape itself to support long-duration missions. Some of the most intriguing features of the gravitational architecture are the low-energy pathways that interconnect Wells and Lagrange regions. These pathways, revealed through advanced dynamical systems analysis, allow spacecraft to drift between planets or moons with minimal fuel expenditure. Known collectively as the interplanetary superhighway, these routes depend on the delicate balance of gravitational forces and the natural contours of spacetime. Though slow compared to traditional transfer orbits, they open possibilities for missions focused on efficiency rather than speed. The Genesis mission used such pathways to collect solar wind samples, traveling through gentle transitions that required precise but low-energy maneuvers. Gravity does not merely bind objects together, it shapes the structure of possibility, defining which missions can be accomplished with existing technology and how spacecraft must travel to achieve their goals. As we map this invisible landscape with increasing accuracy, our ability to navigate it grows more refined. But with each refinement, we discover that the solar system is far from simple. It is a shifting topography of wells, ridges, and equilibrium points, each offering challenges and opportunities that require both insight and respect. The next part of this chapter will explore how mission planners use this gravitational architecture to design trajectories, landings, and orbital operations, revealing the intimate relationship between gravity and the choices that shape exploration. Every interplanetary mission begins long before a rocket leaves the launch pad. It begins with an intricate study of the gravitational landscape it must cross, a landscape filled with wells and contours that determine how much energy the spacecraft will need, how long the journey will take, and which routes are even possible. Mission planners analyze this landscape as if charting an invisible terrain, identifying the slopes a spacecraft can descend, the ridges it must climb, and the regions where gravitational forces balance into fragile equilibrium. These choices define the very architecture of a mission. They determine whether a spacecraft can orbit a planet, land on its surface, or visit multiple worlds in sequence. The gravitational design shapes every calculation, from propellant requirements to engine performance, from flight duration to scientific opportunity. The first major decision involves selecting the trajectory that carries the spacecraft from Earth to its destination. A mission aiming for Mars must consider the shape of Earth's gravitational well, the depth of the Sun's well, and the energy required to descend into and escape from each along the way. Engineers model this journey as a series of transitions. The spacecraft climbs out of Earth's steep well, enters the Sun's more gradual basin, and then descends into the moderate well of Mars. Each transition consumes energy or provides it, depending on the direction and timing of motion. A mission that plans to orbit Mars must expend energy to slow down upon arrival, while a mission designed to fly past the planet may carry that momentum farther into the solar system. These differing objectives lead to different fuel budgets, different engine configurations, and different mission strategies. Landing on a planetary surface adds another layer of complexity. The depth of the gravitational well influences not only how much energy is required to descend, but how that descent can be managed. On Mars, engineers can rely on the thin atmosphere to remove some of the spacecraft's speed, using heat shields, parachutes, and retro propulsion to complete the landing. the famous sky crane system used to deliver the Perseverance rover, leveraged Mars's moderate gravity, strong enough to allow controlled descent, but weak enough to permit complex maneuvers. On the Moon, however, descent requires precision burns because no atmosphere exists to help. Every meter of altitude and every meter per second of velocity must be balanced by thrust. This need for precise control shaped the design of the Apollo landers, which carried descent engines capable of fine adjustments during the critical final moments of landing. Orbiters face their own gravitational challenges. A spacecraft entering orbit around Jupiter or Saturn encounters a gravitational well so deep that even small deviations in speed can have dramatic consequences. To avoid falling too far into the well or escaping it entirely, the spacecraft must perform a burn of precise duration and direction. The Cassini spacecraft executed such maneuvers repeatedly, adjusting its path to thread between the moons of Saturn. Each pass altered its trajectory through the subtle interplay of the planet's well and the wells of its moons. These maneuvers demanded not only detailed gravitational models, but the consistent performance of onboard thrusters, as even slight discrepancies could accumulate into larger navigational errors. Gravity also influences how spacecraft conduct science once in orbit. A craft studying a planet's atmosphere or surface must maintain an altitude that balances observational needs with fuel consumption. Too low in orbit may require frequent reboost maneuvers due to atmospheric drag, especially around planets like Mars, whose atmosphere extends higher than one might expect. Too high in orbit may limit the resolution of instruments or reduce the frequency of passes over areas of interest. The Mars Reconnaissance Orbiter operates in a carefully chosen orbit that optimizes imaging resolution while minimizing the energy required to maintain altitude. This balance reflects the constant negotiation between gravity and mission goals. The gravitational architecture becomes even more powerful when combined with propulsion systems capable of fine control. Missions that rely on ion propulsion can take advantage of gentle, continuous thrust to reshape their trajectories within gravitational wells. The Dawn spacecraft used such techniques to transition between Vesta and Ceres, adjusting its orbit gradually in response to the gravitational contours of each body. This ability to maneuver efficiently within shallow wells transformed the mission from a single target to a multi-destination exploration, expanding our understanding of these ancient remnants of the early solar system. Lagrange points offer strategic positions within the gravitational architecture where spacecraft can operate with minimal fuel. These points serve as gateways, observation platforms, or stable homes for instruments that require consistent orientation relative to Earth or the Sun. Missions positioned at Lagrange points often enjoy long operational lifetimes because they require only periodic station keeping. The James Webb Space Telescope benefits from this stability, allowing it to maintain a clear line of sight to space while staying in thermal balance. This strategic use of gravitational equilibrium enables scientific observations that would be impractical from low Earth orbit or lunar orbit. The gravitational architecture of the solar system also influences how spacecraft eventually depart or conclude their missions. When a planetary orbiter runs low on fuel, engineers must consider how gravity will affect its final trajectory. Missions around giant planets often end with controlled entries into the atmosphere to prevent accidental contamination of moons that may harbor subsurface oceans. The Cassini mission ended with a deliberate dive into Saturn's atmosphere, using the planet's gravity to guide its final descent. This decision ensured compliance with planetary protection standards, while allowing the mission to gather valuable final data. In all these examples, gravity acts as both constraint and collaborator. It defines the energy required for each maneuver while offering pathways that minimize propellant use. It shapes every landing, every orbit, every flyby, and every transition between worlds. The more deeply engineers understand this structure, the more efficiently they can design missions that explore the solar system without exceeding practical limits. This chapter has revealed gravity as the architect of possibility, sculpting a terrain of wells and equilibrium points that determine where spacecraft can go and what they can accomplish. The next chapter will shift from the mechanical constraints imposed by gravity to the biological ones, exploring how the absence or alteration of gravitational forces affects the human body in ways both subtle and profound. Before we step inside the fragile habitat of a spacecraft orbiting high above Earth, consider a question that seems simple yet carries consequences that reach into every cell of the human body. What does it truly mean for your weight to vanish while your mass remains unchanged? What happens when the pull that shaped your bones, guided your blood, and calibrated your sense of balance since the moment you were born suddenly weakens, not because gravity has disappeared, but because you and everything around you are falling together? And if microgravity transforms the human body in ways that are subtle at first and profound over time, then what truths has decades of research uncovered about how we adapt, how we endure, and where our limits truly lie? The moment astronauts enter orbit, their bodies confront an environment unlike anything on Earth. Gravity, though still present at nearly full strength, no longer presses them against the floor or pulls against their muscles and bones. They experience continuous freefall, drifting in a state that reshapes the sensations of motion and balance. Fluids redistribute through the body, rising toward the head as the familiar hydrostatic gradient collapses. Faces puff slightly, legs grow thinner, and the sense of body orientation becomes uncertain. These changes emerge within hours, revealing how deeply gravity has calibrated human physiology across a lifetime. One of the most striking effects of microgravity is bone mineral density loss. Bones rely on mechanical loading to maintain their structure, responding to stress by remodeling and strengthening themselves. When astronauts float without weight-bearing forces, the signals that normally sustain bone density diminish. Studies from the International Space Station show that bone loss can occur at significant rates, especially in the hips and lower spine, regions accustomed to supporting the body on Earth. This loss does not plateau quickly. Without countermeasures, it continues over the course of long missions, reflecting the absence of forces that bones evolved to withstand. Although some recovery occurs upon return to Earth, the process is slow and incomplete for certain bone regions, highlighting the need for effective in-flight mitigation. Muscle atrophy follows a similar pattern. The postural muscles that support the body against gravity weaken without daily load. Astronauts find that simple tasks, like standing or lifting light objects, become challenging upon return to Earth. Research conducted on treadmills and resistive exercise devices aboard the station shows that regular exercise can slow muscle loss, but not eliminate it entirely. These devices use elastic or mechanical resistance to simulate the work normally provided by gravity, allowing astronauts to maintain some strength throughout their missions. Yet even with rigorous adherence, microgravity reshapes muscle fibers, shifting their composition in ways that affect endurance and force production. The cardiovascular system also adapts rapidly to microgravity. On Earth, the heart works constantly against gravity to pump blood upward. In orbit, with fluids distributed more evenly, the heart reduces its workload, gradually shrinking in size. Astronauts' blood volume decreases as the body adjusts to the new environment, altering circulatory dynamics. Upon return to Earth, this adaptation becomes a liability as the cardiovascular system struggles to reassert the pressure gradients required for standing and walking. Some astronauts experience orthostatic intolerance, a temporary difficulty in maintaining blood pressure when upright. Studies using wearable sensors and in-flight ultrasound have documented these changes in detail, offering insights into how the cardiovascular system rewires itself when gravity's constant demand is removed. Microgravity affects the eyes and brain as well. A condition known as space-associated neuroocular syndrome has emerged as a significant concern for long-duration missions. This condition involves changes in the shape of the eye, swelling of the optic nerve, and shifts in visual acuity. Researchers believe that fluid redistribution in the head increases pressure around the optic structures, contributing to these changes. While not all astronauts experience the same symptoms, the variability and potential for long-term effects have prompted extensive study. Experiments aboard the space station evaluate how pressure in the brain and eyes adjusts over time, using ultrasound, optical coherence tomography, and fluid shifting protocols to understand the underlying mechanisms. Beyond structural systems, microgravity influences biological processes at the molecular level. Studies of gene expression reveal that hundreds of genes alter their activity in microgravity, affecting immune response, cellular repair, and metabolic regulation. These changes highlight the adaptability of the body, but also reveal vulnerabilities. The immune system, for example, shows signs of dysregulation, with altered responses to vaccines and latent viral reactivation observed during missions. These findings underscore the complexity of supporting human health in an environment that challenges physiology in ways both broad and subtle. Radiation exposure compounds these challenges. Outside Earth's protective atmosphere, astronauts face a constant flux of high-energy particles from solar activity and galactic cosmic rays. Shielding reduces but cannot eliminate this exposure. Long-duration missions accumulate doses that exceed what is typically encountered on Earth, raising concerns about cancer risk and other long-term effects. The unique combination of microgravity and radiation alters cellular behavior in ways still being studied, prompting research into protective materials, pharmacological countermeasures, and biological markers that can indicate early signs of stress. Sleep patterns also shift in microgravity. The absence of natural day-night cycles experienced on Earth can disrupt circadian rhythms, leading to difficulties in falling asleep and maintaining consistent rest. Light-based interventions and scheduled routines help regulate these rhythms, but the challenge persists. The constant hum of machinery, the confined living quarters, and the awareness of being in an extreme environment all influence the quality of sleep. Studies using actigraphy and onboard monitoring systems evaluate these patterns, aiming to develop strategies that support long-term cognitive performance. Despite these challenges, humans demonstrate remarkable resilience in microgravity. Decades of missions have shown that with proper planning, exercise, nutrition, and medical oversight, astronauts can complete extended stays aboard the International Space Station and return to Earth with manageable, though significant, physiological changes. These experiences provide invaluable data for planning future missions to the Moon, Mars, and beyond. The lessons learned from microgravity research guide the development of habitats, exercise equipment, protective materials, and health monitoring systems that will support astronauts on journeys lasting months or even years. As we understand more about how the body responds to microgravity, a deeper truth emerges. Gravity has shaped human evolution so profoundly that its absence reveals fundamental aspects of our biology. Bones, muscles, circulation, and even cellular behavior depend on the constant pull we experience on Earth. When that pull weakens, the body shifts into a new mode, revealing both its adaptability and its limits. The next part of this chapter will explore the countermeasures developed to support human health in microgravity, the experiments that shaped our understanding, and the strategies that continue to evolve as humanity prepares for longer voyages. The moment the human body enters microgravity, the challenge is no longer simply to observe the changes it undergoes, but to counteract them with strategies that preserve health over weeks, months, or even years. Each countermeasure developed through decades of research reflects a deepening understanding of how gravity shapes physiology. Once astronauts step into an environment where that familiar pull no longer grounds their bodies, everything from their exercise routines to their diet, from their sleep schedule to their medical monitoring, becomes a carefully orchestrated system designed to hold back the tide of physical adaptation that would otherwise proceed unchecked. In this sense, the microgravity environment is both a laboratory and a teacher, revealing how the human body can endure and what limits must be respected as missions grow longer and more ambitious. Exercise remains the primary defense against bone and muscle loss, yet even here the absence of gravity forces innovation. On Earth, walking, running, climbing, and lifting rely on gravity to provide resistance. In microgravity, astronauts must rely on devices that simulate this resistance mechanically. The Advanced Resistive Exercise device aboard the International Space Station uses vacuum cylinders and adjustable load systems to create forces similar to weight training. Astronauts perform squats, deadlifts, calf raises, and other exercises that load the bones and muscles in ways that approximate Earth-based movement. These sessions occur daily and last for extended periods, because the body must be reminded consistently of the forces it no longer encounters naturally. While exercise slows bone density loss and muscle atrophy, it does not eliminate them, revealing the depth of the physiological dependence on gravity. Treadmill exercise introduces its own engineering challenges. Without weight, astronauts cannot simply run. They must be strapped to the treadmill with harnesses that pull them downward, simulating the effect of body weight. The tension of these harnesses must be carefully adjusted. Too little force and the run provides insufficient stimulus. Too much force and the harness becomes uncomfortable, restricting breathing or altering movement patterns. Research has shown that even with carefully calibrated harness systems, gait mechanics change in microgravity, raising questions about long-term musculoskeletal adaptation. These variations offer insight into how deeply the act of walking and running depend on the familiar interplay between gravity, balance, and muscle coordination. Countermeasures extend beyond exercise. Nutrition becomes a tool for forming and repairing tissue in an environment where degradation otherwise outpaces synthesis. Diets rich in protein, vitamins, and essential minerals help support bone remodeling and muscle maintenance. Calcium and vitamin D play central roles in sustaining bone health, but nutrients alone cannot overcome the absence of mechanical loading. Instead, they support the body's capacity to rebuild what exercise and countermeasures stimulate. Research on board the station evaluates how metabolic pathways shift in microgravity, influencing how nutrients are absorbed, stored, and used. These findings refine nutrition programs for future missions, ensuring that astronauts receive not only sufficient calories, but the right balance of macronutrients and micronutrients to support long-duration health. Addressing cardiovascular changes requires both monitoring and targeted activities. Devices that track heart rate, blood pressure, and stroke volume provide continuous insight into how the cardiovascular system adapts to microgravity. Fluid loading before re-entry helps prepare astronauts for the gravitational stresses that return upon reaching Earth, replenishing blood volume and improving the body's ability to regulate pressure when standing. Some studies explore the use of lower body negative pressure suits, which simulate the effects of gravity on blood distribution by creating a vacuum around the lower half of the body. These suits pull fluids toward the legs, prompting cardiovascular responses that counteract the microgravity-induced redistribution. Although these techniques show promise, their long-term effectiveness continues to be evaluated through controlled experiments. Addressing space-associated neuroocular syndrome requires an even more nuanced approach. Because the condition appears linked to altered fluid distribution and possibly increased intracranial pressure, researchers investigate strategies that influence the movement of fluids within the body. One method involves adjusting posture during sleep, using devices that apply slight negative pressure to the lower body. Another explores pharmacological approaches that may modulate fluid retention or vascular behavior. Advanced imaging tools aboard the station allow scientists to track changes in optic nerve structure, eye shape, and blood flow, refining hypotheses and guiding new interventions. Each experiment contributes to a broader understanding of how delicate the balance of pressure and fluid distribution is within the head and eyes. and how microgravity alters that balance in ways unfamiliar to life on Earth. Radiation exposure requires its own set of protections. Shielding aboard spacecraft relies on materials that absorb or deflect high-energy particles, but no shielding can eliminate exposure entirely. Water and polyethylene offer advantages due to their hydrogen-rich composition, which interacts effectively with charged particles. Crew quarters often incorporate additional shielding to reduce exposure during solar particle events. Radiation monitoring devices track cumulative doses, ensuring that astronauts remain within established safety limits. Research continues into pharmaceuticals that might support cellular defense against radiation, as well as materials capable of providing greater protection without compromising spacecraft mass or design. The challenge grows more acute when considering missions beyond low Earth orbit, where exposure to galactic cosmic rays becomes more intense and persistent. Sleep and circadian rhythm management also form an essential part of crew health. Without the natural alternation of day and night, astronauts rely on carefully controlled lighting to regulate their internal clocks. Blue-enriched light promotes alertness, while softer wavelengths support relaxation and sleep. Scheduled routines, exercise sessions, and meal times reinforce these cues. Despite these efforts, sleep disturbances remain common, influenced by the operational demands of spaceflight, noise within the station, and psychological factors associated with confinement. Continuous monitoring through wearable devices helps researchers analyze patterns and refine interventions, recognizing that cognitive function and emotional well-being depend heavily on restful sleep. Psychological health is likewise supported through communication with Earth, structured activities, and private time. While microgravity itself does not directly shape psychological responses, the space environment amplifies stresses associated with isolation, confinement, and constant operational vigilance. Studies in behavioral health reveal the importance of team cohesion, conflict management skills, and regular interaction with family and mission support teams. These findings guide preparation for future missions that will involve even greater isolation, such as journeys to Mars, where communication delays stretch into minutes. Artificial gravity research seeks to address many physiological challenges simultaneously by reintroducing mechanical loading through rotation. Small centrifuges aboard the station allow experiments on animals and biological samples, simulating partial gravity environments. Human-scale artificial gravity remains a topic of study, with concepts involving rotating habitats or short-arm centrifuges designed to apply intermittent forces to astronauts. These ideas remain grounded in physics, but their engineering and operational considerations continue to be evaluated. The potential to recreate gravitational forces in space offers a promising avenue for reducing many of the risks associated with microgravity, though the practical implementation of such systems remains an open question. Each countermeasure, from exercise devices to lighting strategies, from shielding materials to medical protocols, reflects a growing awareness of the complex interplay between gravity and human physiology. Microgravity research reveals that every system in the body responds to the absence of gravitational load, challenging assumptions about how adaptable humans truly are and highlighting where our evolutionary origins impose constraints. As missions extend farther from Earth and last longer, this knowledge becomes essential. The lessons learned today aboard the International Space Station form the foundation for future journeys, ensuring that astronauts are not only able to survive in microgravity, but to thrive long enough to complete the demanding tasks required of exploration. The next part of this chapter will shift toward environments beyond microgravity, exploring how partial gravity on worlds such as the Moon and Mars influences physiology, and what research reveals about human performance under these new and unfamiliar conditions. The transition from microgravity to environments with partial gravity reveals an entirely new dimension of human adaptation, one that sits between the weightless drifting of orbit and the familiar pull of Earth. Worlds such as the Moon and Mars introduce gravitational forces that are weaker than Earth's, but strong enough to influence walking, circulation, balance, and long-term physiology in ways researchers are only beginning to understand. Unlike microgravity, where the absence of load produces rapid and well-documented changes, partial gravity environments raise questions that cannot yet be fully answered because no human has spent extended periods living under these conditions. The International Space Station has provided decades of data for microgravity, but the Moon's 1/6 gravity and Mars's roughly 1/3 gravity remain largely uncharted territories for human biology. Yet these are the environments where future explorers may live for months or years, making the study of partial gravity essential for planning sustainable missions. Experiments conducted on parabolic flights, drop towers, and short-arm centrifuges suggest that partial gravity may slow some of the physiological changes observed in microgravity, but not prevent them entirely. Bones that lose density in orbit might degrade more slowly in partial gravity, but without Earth-level loading, the signals that promote bone formation remain diminished. Muscles that weaken in microgravity may retain more strength under reduced gravity, yet the reduced load could still lead to gradual atrophy unless countermeasures are consistently applied. These early findings indicate that the spectrum of physiological adaptation is not binary but continuous, shaped by the degree of gravitational force applied to the body over time. Walking and movement under partial gravity introduce challenges that extend beyond strength alone. On the Moon, astronauts during the Apollo missions found that hopping or loping proved more efficient than traditional walking. The reduced gravitational pull altered their sense of balance, causing them to tilt or drift more easily. Video analysis of those missions shows subtle oscillations in posture and foot placement, revealing how deeply Earth's gravity has shaped human locomotion. While Apollo missions provided valuable insight, their duration was too short to reveal long-term changes in gait mechanics, coordination, or neuromuscular control. Living for months under lunar gravity would likely reshape movement patterns even further, and this remains an open area of study. Circulation under partial gravity also presents unanswered questions. In microgravity, fluids shift upward toward the head, while on Earth, gravity pulls them downward toward the legs. Partial gravity would create an intermediate distribution, altering blood pressure gradients in ways researchers cannot yet predict with confidence. The cardiovascular system might adapt by adjusting vessel elasticity, heart size, or regulatory mechanisms that control pressure. Understanding these adaptations is critical for preventing dizziness, fainting, or long-term circulatory challenges as astronauts transition between environments. The vestibular system, responsible for balance and spatial orientation, undergoes significant adjustment in microgravity and would likely respond differently in partial gravity. On Earth, the inner ear interprets signals from gravitational pull to determine orientation. In microgravity, conflicting sensory inputs create temporary disorientation, motion sickness, and altered perception of movement. In partial gravity, the vestibular system would receive signals that are weaker but still present, requiring the brain to recalibrate its interpretation of motion. This recalibration could influence everything from everyday movement to the operation of machinery, making it essential to prepare astronauts for a wider range of gravitational cues. Countermeasures developed for microgravity may require adaptation for partial gravity environments. Exercise equipment designed for weightlessness may not function optimally under low gravity, where body weight exists but remains insufficient to stimulate bones and muscles effectively. New devices may need to apply artificial loading that compensates for the reduced gravitational force. Habitat design must also consider ergonomic factors. Sleeping arrangements, seating, walking surfaces, and workstations must accommodate bodies that are lighter but not weightless, ensuring comfort, safety, and efficiency. Even basic tasks such as cooking, hygiene, and waste management require rethinking when gravity is present but weakened, influencing how fluids behave and how objects settle. Radiation exposure remains a significant concern on the Moon and Mars, where the lack of a thick atmosphere or strong magnetic field exposes astronauts to higher levels of cosmic radiation than on Earth. The Moon's lack of atmosphere offers no shielding, requiring habitats to incorporate regolith-based barriers or specialized materials to reduce exposure. Mars offers some atmospheric protection, but not enough to fully mitigate radiation risks. Understanding how partial gravity interacts with radiation effects, cellular repair mechanisms, and overall physiological resilience is vital for designing missions that last beyond short expeditions. Sleep and circadian rhythm regulation also become more complex in partial gravity environments. On the Moon, day-night cycles last nearly a month, creating extended periods of light and darkness that challenge biological rhythms. Mars offers a day length similar to Earth's, but its weaker gravity and reduced daylight intensity could still disrupt sleep patterns. Research into lighting systems, habitat design, and daily schedules will play a central role in maintaining cognitive performance and psychological health during extended stays. Psychological adaptation in partial gravity environments introduces unique aspects as well. The presence of gravity may ease certain stresses experienced in microgravity, such as the constant sense of drifting or the difficulty of orienting oneself spatially. Yet new stresses will emerge. The monotony of reduced gravity movement, the constraints of small habitats, and the long separation from Earth all contribute to mental strain. The ability to step outside onto a planetary surface, even in a protective suit, may counterbalance some stress by restoring a sense of grounding and connection to the environment, revealing how deeply humans rely on physical context for psychological well-being. Ultimately, partial gravity environments represent the next frontier in human physiological research. Microgravity studies have laid the groundwork, revealing the plasticity and vulnerability of the human body when freed from Earth's pull. But partial gravity will show how the body recalibrates when gravity is diminished but not absent. These environments may offer enough load to preserve certain functions while still allowing others to drift from Earth-based norms. Understanding where these boundaries lie will determine how long humans can live on the Moon, how sustainable a Mars colony may become, and what preparations future explorers must undergo before leaving Earth. As this chapter concludes, the intricate relationship between gravity and physiology becomes increasingly clear. The next chapter will shift our focus from the human body to the bodies of worlds themselves, exploring how gravity shapes surfaces, atmospheres, and environments across the solar system, and how these differences define the challenges and opportunities awaiting future explorers. Gravity reveals its character most clearly when you leave Earth behind and step into environments shaped by different masses, radii, and histories. The Moon pulls with only 1/6 of the strength you feel on Earth, and astronauts who walked there described a strange buoyant rhythm in every step, a gentle drift that followed each movement. This effect arises not from imagination, but from precise measurements collected by orbiters, landers, and laser-ranging experiments that map the Moon's gravitational field with remarkable detail. Dust lifted from a boot did not fall as sharply as on Earth. Instead, it traced long, shallow arcs shaped by the weaker gravitational pull. Even the fine grains of lunar regolith behaved differently as they settled around equipment, responding to lower weight and electrostatic forces in ways that surprised engineers who had tested simulants on Earth but could not fully anticipate conditions on the surface. Mars, with gravity close to 1/3 of Earth's, tells another story. Rovers that crawl across its terrain move with a confidence granted by reduced weight, yet they must contend with slopes and dust that behave with a subtle unfamiliarity. The thin Martian atmosphere, combined with gravity lower than Earth's, allows dust to remain suspended for long periods, feeding storms that wrap the planet in a reddish haze for weeks. Landers descending toward Mars encounter gravitational and aerodynamic regimes, unlike any tested on Earth. Parachutes deploy later and slow the craft less effectively because the air is too thin, yet gravity still pulls with enough strength that retropropulsion must complete the landing. Each mission from Viking to Perseverance has demonstrated that navigating the Martian environment means working within gravitational parameters measured by orbiters and surface instruments. Far smaller worlds reveal gravity at its most delicate. Asteroids like Bennu possess such weak gravitational fields that a human could leap from the surface and never return. The OSIRIS-REx spacecraft approached Bennu at walking speed because anything faster risked bouncing back into space. Dust disturbed by the sampling arm drifted slowly, following trajectories governed by a gravitational pull barely stronger than a whisper. These conditions remind explorers that gravity is not merely a force, but an identity. Every world expresses it differently, and missions succeed only when these subtle signatures are understood and respected. Even moons with dense atmospheres, such as Titan, present environments shaped by gravity that differs from Earth's, yet offers new possibilities. Titan's gravity is lower than the Moon's, but its atmosphere is thicker than Earth's. The combination makes movement easier and flight more feasible with minimal mechanical assistance. The Huygens probe's gentle descent through Titan's atmosphere became a lesson in how planetary gravity interacts with atmospheric density, creating a landing environment unlike any other explored in the solar system. Gravity defines terrain, mobility, and the behavior of dust and rock. It shapes lander design, rover mechanics, and flight trajectories. It influences how explorers will build and move and work on every future world. As we turn toward deeper space, the next chapter reveals how gravity shapes not only surfaces and motion, but the fabric of time itself. Relativity enters exploration quietly, almost invisibly, yet nothing beyond Earth functions without it. Time flows differently in orbit than on the ground. Light bends as it passes near massive bodies. Signals stretch and shift as spacecraft move at high speeds. Each effect has been observed, measured, and woven into the systems that guide space missions. The theory that once seemed abstract now forms the backbone of navigation, communication, and timing across the solar system. The Global Positioning System offers one of the clearest demonstrations. Satellites orbit Earth, where gravity is slightly weaker than it is on the surface. Their atomic clocks tick faster as a result. At the same time, their orbital velocity produces a time dilation effect that slows the clocks. The two influences do not cancel. The gravitational effect dominates, meaning the satellite clocks run ahead of Earth-based clocks by tens of microseconds each day. Without corrections based on relativity, the positions calculated by receivers on Earth would drift by kilometers within hours. Every car, aircraft, and ship that relies on this system depends on Einstein's equations being applied with precision. Relativity also shapes communication with deep space probes. When a signal travels near the Sun, space-time curvature slows its journey, producing a delay that engineers must account for when calculating distances. This Shapiro delay has been confirmed repeatedly through spacecraft ranging experiments. Even the slight bending of radio waves passing close to the Sun influences how antennas track signals. Navigation teams incorporate these deviations because ignoring them would cause trajectories to drift over long periods. Spacecraft near massive planets also reveal the subtle influence of curved space-time. Juno's orbit around Jupiter experiences tiny deviations from Newtonian predictions, deviations that allow scientists to refine models of Jupiter's interior structure. These small discrepancies become tools for exploring the deep, unseen layers of a giant world, demonstrating that relativity is not merely a correction, but a means of extracting information. The detection of gravitational waves pushes relativity into an even more dramatic realm. Observatories on Earth have recorded space-time stretching and compressing as waves from distant black hole mergers sweep past. These measurements confirm predictions made a century earlier and reveal that space-time is not static but dynamic. Though spacecraft cannot yet detect such waves directly, future missions will use formations of satellites to measure them across millions of kilometers, turning the solar system into an observatory sensitive to the faint rhythms of the cosmos. Relativity underpins every precise measurement across the solar system. It governs how clocks stay synchronized, how spacecraft locate themselves, and how scientists interpret signals from worlds near and far. As we turn to the next chapter, we reach a boundary not of imagination, but of evidence, exploring what physics allows us to consider and where the universe draws its limits. At the frontier of physics, ideas expand outward, but evidence pulls them back into alignment with reality. The universe offers freedom to explore, but not freedom to ignore what has been measured. As theories reach for deeper explanations, they must satisfy observations from particle colliders, telescopes, gravitational wave detectors, and cosmic surveys. Anything that contradicts data dissolves, and anything that remains untested must wait for experiments capable of revealing truth or refutation. General relativity and quantum mechanics both stand on firm empirical ground, yet they do not merge naturally. The search for quantum gravity explores this gap through frameworks such as loop quantum gravity and string theory. These frameworks offer possible descriptions of space-time at unimaginably small scales, but none have been confirmed experimentally. Their predictions lie far beyond the reach of current accelerators, leaving them as mathematical possibilities rather than physical conclusions. Theoretical constructs that rely on negative energy or exotic space-time geometries remain constrained by observation. The Casimir effect shows that quantum fields can produce tiny regions of reduced energy density, but nothing close to the sustained negative energy required for traversable wormholes or warp metrics. These ideas remain mathematically interesting, but unsupported by laboratory evidence. Dark matter and dark energy stand as powerful reminders that physics advances through observation. The rotation of galaxies, gravitational lensing of distant light, and patterns in the cosmic microwave background all point to unseen components shaping cosmic evolution. Experiments search for particles that might constitute dark matter, while cosmological measurements refine our understanding of dark energy's influence. These mysteries persist, not because physics is incomplete, but because nature reveals itself in stages, and instruments must catch up to the scale of the questions. Nothing in known physics permits faster than light travel or communication. Quantum entanglement creates correlations that appear instantaneous, yet no information passes between particles faster than light. Relativity remains intact. The speed of light stands as a limit supported by every experiment ever conducted. The boundary of physics is not a wall, but a narrowing corridor where new theories must pass through the filter of evidence. Everything beyond that corridor remains possibility, not reality. As we approach the end of this book, the final chapter turns toward humanity's future, not through speculation, but through the steady unfolding of what physics makes possible. The story of humanity's expansion into the solar system will unfold not through defiance of physics, but through mastery of it. Every world we approach, every craft we build, every habitat we raise will exist within the framework of energy, motion, and gravity. The future becomes clear when we recognize that gravity is not the enemy of exploration, but its guide, shaping every challenge and every achievement. The moon will become our first workshop beyond Earth, a place where 1/6 gravity teaches new rhythms of movement and construction. Mars will follow, a frontier where 1/3 gravity reshapes physiology and daily life. Robotic explorers will push outward to the icy moons, where gravity reveals hidden oceans beneath layers of ice. Spacecraft will roam the outer planets guided by models of space-time curvature that keep them on target even as distances grow immense. Electric propulsion, nuclear thermal engines, and autonomous navigation will transform long-duration missions. In situ, resource utilization will turn distant worlds into sources of water, fuel, and shelter. Radiation protection strategies will mature through layered shielding, underground construction, and refined operational planning. Each innovation remains grounded in measurable physics, not speculation. One day, lightweight probes may accelerate toward nearby stars using powerful Earth-based lasers. They will not break the speed of light, and they will not warp space-time. but they will cross interstellar distances over decades, carrying instruments that expand humanity's reach while obeying every boundary nature has set. The ending of this book is not an ending to exploration. It is an acknowledgement that physics lights the path ahead. Gravity, once the first barrier we learn to overcome, becomes the quiet architect of possibility. It shapes landscapes, trajectories, habitats, bodies, and time. It guides every future step across worlds we have not yet seen. Our future in space is not limited by imagination. It is defined by the laws of nature, and within those laws lies a universe large enough for countless generations of explorers. As long as we move forward with evidence as our compass and physics as our foundation, the cosmos will never be beyond our reach.